new package is called Screencast-O-Matic, and it records everything that's projected and everything that I say. But I have to tell it where to send it, and what works best is sending it to YouTube. Okay? Now, rather than you have to search around on YouTube for it, what I've done is put it in what they call a playlist, which is like a directory, and then you just go to the playlist and you can pick up the class you missed or whatever. And the reason I'm saying this is for people who weren't here last time, either left early or weren't here at all, you can pick up anything you missed there. And how do you find it? Well, let's start with a little bit on Blackboard. All of you are familiar with Blackboard, right? Somewhatly anyway. When you go to this class in Blackboard, there's a set of tabs over here in the upper left corner. I can't remember. In fact, I don't even know for sure because all I see is the instructor side. I don't see the student side. But on the instructor side, it's like the second or third tab there. It says Content. So if you click on Content, then you'll see Open Up the Syllabus. Okay? I did find, I think, one little thing in the syllabus I probably got to correct, but I may have a chance to do it tomorrow. But it's not a major thing. It's just a small thing. Then you'll see the research paper instructions. Now, I don't think there's any changes there. Those should be good. Then you'll see my locator card. Now, I know there's one change on the locator card, so I will try to get that done and corrected. So that will be the next. And then I think the next thing out there is the link to YouTube. So if you just click on that link, it takes you to the playlist. And right now, that one file, last class, is on there. Now, what I said, you get what you pay for. When we had Tegrity, if you went to open that, then you would see every slide that I did either on PowerPoint or every screen that I did on anything else, and you could pick the one or wherever you wanted to listen to and just listen to those. With this one, you either have to listen to it all or you just have to guess where there's a bar down there, and you can tell it to go there and then guess. So you get what you pay for. Okay. They pay for it. Okay. So anyway, it's there. So you can hear, you can see and hear just about everything we did in class on Tuesday. Okay? All of you can. Those who had to leave early or those who weren't here. So you can catch up and be there. Now, I will take the computer to the lab and I'll record as much of the lab as I can. But in the lab, you're actually going to be taking measurements and recording things and writing things down, and I'll be answering questions and talking, but there's no way I can record everybody's answers because all of you will have different measurements, or each team will have different measurements. So if you can't be here for lab, you need to get with someone who was there and try to get the data and get as good of understanding as you can, because some of that may be showing up on the test as well. Not usually much, but especially this first lab, there will be some very similar things. It's stuff we've done in class, but it was also reinforced in lab. So let's talk about that. Like I said, we'll probably finish chapter 1 today, probably pretty early in the period. The class goes from now till 5:45. 5:45 we'll go down to the lab, over to the lab, just right down the hall here, if we can use that one. I haven't figured out whether there's a biology class in there or not then or not, but we'll find out. Then we will do the lab, and then when you finish the lab or we run out of time once, 7:45 gets here, hopefully you'll finish by then, that'll be it for today. Since we'll probably finish the chapter today, that means Tuesday, the last 30 minutes of the class will be your test on chapter 1. Even though we'll be in chapter 2, the first part of the class, and we may even be far enough along to have the second lab. We'll do that for the next 2 hours. If we're having a test and a lab, then we'll actually end class 30 minutes sooner, so we can have 2 hours for lab, and then 30 minutes for the test. So that's how we'll be run. Class, if we're doing a lab, lab, and if we're doing a test, test. I always will give you 2 hours for lab. If we have a test at the end, that's 30 minutes. So I'll just move up, and rather than 5:45, we'll start the lab at 5:15. Understood? Any questions about that? Okay. So let's pick up where we left off last time. I think we had done the density ratio already. Okay? So why it came back here, I don't know. Okay, this is where we start today. Symbols and equations. Any questions on anything we did up till now? If you've got your text, and I know there's different editions of the text out there. This is around page 10. It's chapter 1. Just look for symbols and equations. All right, now we've already run into some of these. Symbols represent the quantities or the measured properties. For instance, mass. We put something on a scale, we measure the mass. Usually the symbol for that, what we've been using, is little m. Not to be confused with the unit for length in the metric system, which is meter. That has to have a number in front of it. 7 meters, 4 meters, 3.2 meters, something like that. Nor to be confused with the m for milli, which could be millimeters, milligrams, whatever. Again, that would have a number in front of it. If you just see a little m, especially in an equation, that stands for mass. Okay? Capital V stands for volume. Little v, we haven't done it yet, but I mentioned it last time. Second, velocity. Very good. Rho, that things that looks like a P, that stands for? Second? Density, exactly, especially mass density. Okay? Those are the main ones we've hit so far. We'll see many more. Symbols represent the quantities. So you don't have to spell out the word. You use a symbol to represent them. Most of the time they're related, but not always. Like rho, where does that get that for density? I don't know. Just probably in the Greek. And here's, by the way, I guess I should say this. In the old days, as in when Isaac Newton was doing his writing and that kind of stuff, they considered Latin to be the language of science. So when he wrote his thing, he was English, but when he wrote his treatise on the principles of mathematical philosophy, is actually what he called it, which meant science, he wrote it in Latin. Okay. Boy, I couldn't have been a scientist back then if I had to learn Latin. So it could be that the Latin word for density started with whatever the equivalent was of the Greek symbol rho. So that may be why it came there. Who knows? Okay. So those are symbols. Okay. Represent quantities or measured properties. Equations give the relationship between those. What was the equation we just used? That used the three I just asked you about? Rho, m, and v. What equation would that be? Yes, rho is equal to m over v. There is your equation. That's a capital V, by the way. Okay, it's hard to tell. It's the only thing there. That is an equation. It represents the relationship between density, mass, and volume. Now, remember this, folks. Units are your friends. If you have a formula like this, then your units had better match up. So what is mass usually measured in? Especially SI. What's the unit for mass in the SI system? System International System. Second? Yes, kilogram. And what's volume measured in? Second? I can't hear.
Liters. He said liters.
Meters, not quite. Meters measures the distance. Liters. Now, that's a very good thing. Sometimes volume is measured in liters. Okay? Cubic feet would be one, but if we're SI, we wouldn't use feet, we would use meters, cubic meters. So kilograms per cubic meters would be sufficient. That would be good units for a density. If you did a calculation and came up with other units, you've probably done your calculation wrong. So you see the units help you check on whether you've done the right multiplication or division or whatever. Now, since...
So you say V is volume, is kilo,
capital V is volume.
and it's equal to kilo.
Okay. All right. These are the symbols, rho, M, and V.
Correct.
They stand for density, mass, and volume. They represent quantities. Now, the units for mass, say you put it on a scale and measured 15 kilograms. That would be huge, okay, by the way. 15 kilograms per, that would be a huge volume, so many cubic meters. Then the units would be whatever that came out being, kilogram per cubic meters. Now remember I said a cubic meter is a huge quantity. It's the block that would be represented by the doorknob down, pretty much that's a meter, a square meter, and this would be pretty close to being a meter out. If we had a big block that big, full of water, that would weigh a ton, very close to a ton. So a kilogram per cubic meter, that's a pretty large number. So quite often for smaller things, like we'll be doing in lab, we'll use a smaller unit for mass. Still in the metric system, what would that be?
Centimeters, millimeters.
Okay, this would be cubic centimeters here, that's volume. What would be your mass? Not kilograms, but grams per cubic centimeter. Okay, that's what we'll be using in lab. Or grams per milliliter. A milliliter is exactly the same as a cubic centimeter. Now, I happened to think of something after we left Tuesday night, that I didn't remember to say. It's sort of an illustration, but it has to do with the, volume, when you're talking about, say, liquids or other things like this, or displacement, quite often we call that capacity. It's still a volume, and that's what we measure liters and quarts and gallons and things like that, to separate it from cubic meters and cubic inches and cubic feet and that kind of stuff. So that's usually called the volume, where they're both volumes, or usually when it's liquid, we talk about capacity. You mentioned, or someone mentioned liters. What is a liter close to in the U.S. customary or British system, English system? What is the unit closest to? A liter. Not a pint, bigger than a pint. A quart. They're very, very close to the same. A liter is a little bit more than a quart. And the thing I remember when I was in college, I was in Navy ROTC, Naval Reserve Officer Training Corps, and I was at Georgia Tech, and I was lucky enough to be on a scholarship with them. This was during Vietnam. They were giving anyone who would go in just about a scholarship, but not quite. But anyway, I had to go on 3 what they called midshipman cruises. One each summer between, first one between my freshman and sophomore year, next one between my sophomore and junior year, and the third one between my junior and senior year. That freshman midshipman cruise, or third class midshipman cruise is what they called it. I was sort of lucky. I got to go up to Little Creek, Virginia, get on an amphibious Navy ship. And the amphibious Navy, they're the ones who land on the beaches and stuff like that. I think the classroom next door is available, so you can probably go there. Okay. By the way, that reminds me, I didn't mark. Y'all remind me when you come in like this, Lakeisha, right? Okay. Has anyone else come in since I called roll? I remember seeing you, but I forgot to stop and mark. Okay. So I took the bus up to Little Creek, Virginia, where I was on an amphibious Navy ship. And of course, the naval ships have designators, like an aircraft carrier is a CVA, and an ammunition ship is an AE, so they all have letters. Well, the amphibious Navy uses the letter L, okay? Anything in the amphibious Navy starts with L. And they have landing, let's see, oh boy. Well, the helicopter assault ship was an LPH or something like that. They all have names. Well, I was on a landing ship's dock is what the name of the ship was. They had other things. Of course, the abbreviation for that was LSD. And my dad, weird sense of humor, enjoyed telling everybody that asked. They said, well, how's Charles doing at school? Oh, he's on an LSD trip this summer. So he got a big kick out of telling people that. Ruined my reputation, by the way. Okay. But anyway, I got on, and it happened to be a sort of, in fact, my orders were for the USS Donner, which was one of the 3 oldest LSDs left in the Navy. They had been in World War II, and they were only 3 of them left. I was assigned to the Donner, but before I got there, the Donner it was so old it broke down, and they couldn't get it repaired, so they were preparing to take it out of commission. So I thought, oh, I'll get on the Nero. Well, no, I was put on the Fort Mandan, which was the second of the 3 oldest LSDs left in the Navy. So I still was on an old ship. I spent most of the first 2 weeks chipping paint on a ship that was rusting. No, I mean, it was an old ship. And I remember I was chipping paint in one place, and suddenly I could see through to the other side. I said, Chief, do you want me to keep chipping? He said, no, let's leave that one alone. So move on somewhere else. It was an old ship. And then, anyway, we were lucky. We got to, after the 2 weeks in the port there, the next 2 weeks were spent crossing the Atlantic. And let me catch your name, please. Patrick, got it. Okay, I've just got to, there you are. Got it. Whoops. Can't write with the ionizing pen. There we go. There we go. Good deal. So I was on, next 2 weeks we were crossing the Atlantic, and that was sort of fun until right toward the end when we ran into a storm, and that wasn't too fun to be on a rocking boat like that. No, that was actually, we got to stop in Azore Islands, which were beautiful, fantastic place. It was really nice. Then we went from Azores to Spain, but there we hit the storm in transit there. It wasn't too much fun on the good old gut, but anyway. Then we went and landed in Rota, Spain, and those were my first 2 times out of country ever. And when they got us on the boat, because we were leaving the ship, and they were going on a Mediterranean cruise. We unfortunately couldn't get into the Mediterranean. We were going to get on the ship they replaced and go back across the Atlantic again. What a fun trip. And that happened to be the San Marcos, which is the 3rd of the 3 oldest LSDs left in the Navy. So I got to be on 2 out of 3 and missed the other one. But anyway, when we were in Rota, Spain, they were taking us to the midshipmen to stay until the other ship, the San Marcos, got in. So we were riding on a bus around the base, and I had heard that this was back when gas prices were beginning to go up. And people were complaining about gas prices and stuff like this. And I had heard that in Europe they were already way higher than the U.S. anyway. So I was sort of watching for that to see. And we were on the U.S. Naval Base in Rota, Spain, and I looked and saw a service station over there. I happened to notice the price, in big letters there, and it wasn't far off from what it was in the States. And I said, oh, this is U.S. military. They probably pay the same price as you do in the States. Until I got closer to it, and then saw that that was per liter, not per gallon. So that was basically close to 4 times as much. And this was on the naval base where the prices were cheaper than out in the society. I thought, had to be from the USA, okay, because we were paying close to a quarter of what they were paying on the naval base in Rodas Bay. So a liter, very close to a quart. In fact, if you were to compare them, pour a liter of milk into a quart bottle, you're going to spill a little bit. Pour a quart into a liter container, you'll have a little bit of headroom left. So when you drink a liter of Coke, that's more than a quart of Coke. What is in your bottle there? Does it say? It's 1 quart?
Yeah.
Okay, does it have a label for liters beside it?
946 milliliters.
946 milliliters. And how much would be 1 liter? How many milliliters?
No.
1,000. So it's only 54 milliliters short, right? Very close to a liter is very close to a quart. If you were to pour that into a liter container, you'd have a little bit more left over. If you tried to pour that into, a liter into that container, you'd spill a little bit. Okay, so those are close. Just one dumb story. Okay. So equations represent mathematical relationships between the properties, and they can describe the properties, define the concepts, and specify those relationships. And what's more, the units are your friends, okay? Don't leave off the units. Anytime you give me a number, pretty much, it needs to have units with it. And if the units don't make sense, that means probably the calculation didn't make sense. You probably did something wrong. Okay. Yay! This is being cheers to everybody. More math. Okay. We're going to talk about 2 types of what we call proportionalities. Okay, now I think we mentioned last time when you have one number divided by another number, what do we call that? Second? Yeah, it can be a proportion, but before it's a proportion, it's a, didn't we talk about? Ratio. Okay, I read your lips. Speak up. Okay, all right. A ratio. One number compared to another. And we use a few examples, right? If you drive 60 miles from here to Tuscaloosa, is that approximately right? Something like that. And you do it in 1 hour. Guess what your speed was? 60 miles per hour. That's a ratio. Distance per time. And the density, mass per unit volume. That's a ratio. Okay? Now, a direct proportionality, what a proportionality is that one ratio equal to another ratio. That's what makes a proportion. Now, get your name, please. Mika, I knew that. Okay. Who, has anyone else come in since roll? Okay. So that's what a proportionality says. Setting one ratio equal to another ratio. So here you have something per something equals something per something. Now, what a direct proportionality tells you is that when one thing increases, the other one increases. Or when one thing decreases, the other. That's what makes it direct. Okay, let's take that trip to Tuscaloosa. Or you're heading west on 2059. Okay? If you drive for 1 hour, you may get 70 miles. If you drive 2 hours, you go 140 miles. So you increase the time, you increase your distance. That's a direct proportionality, right? Now, okay, just hang on to that concept. The second of these is inverse proportional, okay? That means if one increases, the other decreases. Or if one decreases, the other increases. They go in opposite directions. So let's do it this way. If you drove 70 miles per hour on the way to Tuscaloosa, how much time would it take you to get there? Say a little less than an hour, right? If you drove 60 miles an hour, that's decreasing your speed, what happens to your time? It increases, of course. So that's an inverse proportional, okay? One's going up, the other's going down. Inverse proportionality. Now, when you have those, what changes a proportionality to an equality is a proportionality constant. So when I say, for instance, that distance is proportional to time, we said that, right? That the longer you drive, the further you go. That makes sense. Distance is proportional to time. And by the way, that's not a very pretty looking proportionality symbol, but that is a proportionality symbol. Probably, let me try to make it a little prettier than that, okay? I don't draw pretty well at all. It's a little bit more maybe like this. Something like that. Proportional, okay? That's still pretty ugly. Okay, that's it proportional to. What if I wanted to make that an equal to? I need a proportionality constant. Can anyone think of what that proportionality might be? D is equal to something times time. We said it just a short time ago. What do you multiply by time to get your distance? Speed. Okay, I'm going to call it velocity, that little v. Okay? That is your proportionality constant. It changes the proportional to equal k, or some constant. This constant happens to be v. Okay? And that makes it actually an equation. So that's the proportionality constant. It changes proportional to equal k, equal some constant. In this case, it happened to be v. Okay? The other one was that, what do we say? Time is inversely proportional to speed or velocity. Isn't that what we said? The faster you drive, the shorter it takes you to get there. The slower you drive, the longer it takes you to get there. Oops. That should have been a proportional to, and y'all didn't catch it, did you? Okay. Well, it won't erase. There we go. Okay. That should have been a proportional to. And again, I don't draw these symbols very well. Something like that. That's better than the others anyway. Proportional to. Time is inversely proportional to, that's why it's inverted, 1 over the velocity. Well, guess what? We need to make that an equal sign. T is equal to K over V, equal to a constant. Now, what constant might that be? Time is equal to something divided by, you know what, I'm going to make it easier, okay? Let's go back and change this. Okay. It says the same thing. We'll say velocity is equal to 1 over time. Proportional to, inversely proportional to time. Velocity is equal to something over time. What would that something be? Speed is equal to something over time. Distance, exactly. Miles per hour, distance per time. So that constant would be either K or D. There, your distance is your constant of proportionality to that equation. Really, it comes from the same source. So that's what proportionality constants. When you have a direct or an inverse proportionality, putting a constant in there changes it from proportional to equal to. Okay? Many other examples of this. Okay? Now, I'll probably need to erase that. Let's go on here. Now, numerical constants. These two we happen to have here are not strictly numerical constants. They are numerical. Whatever your speed is, it's a number. The distance, that's a number. But they have units as well. Speed would be, say, miles per hour, kilometers per hour, feet per second, meters per second, something like that. Distance could either be miles, kilometers, meters, feet, whatever. So they have units. But sometimes they're purely numerical constants. We'll do one in lab this afternoon that's strictly a numerical constant, meaning it has no units. Other times they'll actually have units, and sometimes the units are, rather than called a ratio, it will be called a rate. Okay? Speed is a rate, the time rate of change of your displacement. Okay? So sometimes there are numerical constants with units. sometimes called rates. Other times they're numerical constants without units, and those are usually the proportionality constants just to make the ratio. Okay. Now, let me get the writing off of there so make it a little easier to read here. Here's the example I just did. If A is directly proportional to B, whatever those are, see there's the symbol, almost as pretty as mine, right? Okay. Okay. A is directly proportional to B, that means as B increases, A also increases. Why they have them written here. And as B decreases, A also decreases. Those are direct proportionality. Is proportional to. If you wanted to make that an equation, equal sign, then you have to introduce the proportionality constant. And let's see if they do that. I don't know if they do. No, that's the inverse. Well, let's go and do inverse first, because that's what they talk about next. Inverse proportionality is like this. As A decreases, B, or as B increases, A decreases, or as B decreases, A increases. They go in opposite directions because they're reverse of each other.
Which one is that?
This is inverse proportionality. Okay? This one is inverse proportionality. And that is still the proportional sign there. Now, think of this. Give me a fraction, any old fraction. 5/8? Is that what you said?
Yes.
Okay, 5/8. What if I increased that denominator and made it 5/16? What have I done to the size of that? Made it smaller. You increase the denominator, you decrease the thing on the other side, right? So, yeah. And vice versa. If I went from 5/8 to 5/4, what does happen here? That made it bigger because it's 1 1/4. Okay, so yeah, got to be bigger. So that's basically what's going on in an inverse proportionality. Okay? Now, this is what they have this rather weird. Let's go back to that one. There's your proportionality. You put a constant in there, proportionality constant, you make it an equality there. Not. So with the proportionality constant here, the two sides are now equal, not just proportional to. And that K is proportionality constant. It could be like distance is proportional to time. That proportionality constant would be velocity. It's multiplied. Okay? I don't think they do one for the other one. Let's just see. No. They left off the one.
Can you go back to that?
Sure. That one? Okay, sorry. Sometimes I go too fast. Be sure to stop. Slow me down.
Okay.
All right, good deal. And the other one, that A is proportional to 1 over B, put the equal K there, it'd be A is equal to K over B. We already sort of did that. We did things we could think about rather than just letters. Okay, any questions on that? More math, good stuff, huh? Okay. Now, they skipped some stuff here, and it's not bad that they do, but it's, I don't know. There's a nice little blurb here on concepts applied, inverse square relationship. You'll hear this sometimes in, maybe not everyday language, but in some things, and you might think, what in the world are they talking about there? Can anyone tell me what follows, something that might follow inverse square law? Have you ever heard that? Okay, maybe not. Let me give you an example. What's that? What was that?
It says energy and distance, light, sound, force, electric fields,
Boy,
radiation.
a ton of things follow inverse square law. I was going to give you an example of light. My wife likes to read at night or in the morning when it's dark, you know, in bed. She has this little clip-on light that goes over her either book or Kindle, and she just clips it on there and she can read. and it's quite bright and reads pretty nicely, okay? Well, what if we hung that from the ceiling? Would it work as well? Okay, because the light intensity falls off not directly. It's like you get twice as far away, it's half as bright. You get twice as far away, it's only 1/4 as bright. It's an inverse relationship. The further you go, the dimmer it gets. But it's not a direct proportionality. It's inversely proportional to the square of the distance. You get twice as far away, it's only 1/4 as bright. 3 times as far away, only 1/9 as bright. Okay, this is how a lot of things go, and several things you just read about. Magnetism, electric fields. Lots of things follow the inverse. And sound. If you get twice as far away, you're only able to hear 1/4 of what you could if you were half the distance. Okay, so that's a nice little blurb, and the illustration there is a really nice one, that when you double the distance, you see it's four times the area there, so any little block is 1/4 of the intensity you had before. There's another little blurb here, not blurb, a section here, on how to solve problems. And we will be doing, remember in the syllabus, the course, not the course description, but the student learning outcomes, I phrased in terms of solving problems. That's what it's all about. Science and everything, solving problems. And up here, again, a gasoline example. The volume of fuel you've added to the tank is directly proportional to the time that you've had the pump running. That makes sense, doesn't it? Yeah. The longer you pump, the more gas you're putting in there. Direct relationship. So, they're saying here at the bottom of page 11, and then carrying on, how to solve problems. Now, these steps aren't hard and fast, and you can rearrange them some if you want to, but generally the flow. And you see this in a lot of math books and a lot of science books. First thing to do, read the problem, okay? Read it carefully. Maybe read it a few times. And as you read, and this is something I like to do, I like to, as I read, jot down the information they give you, okay? Quite often using the symbols like M for mass and V for volume. Remember when we did the problems at the end, of class last time? Wrote down mass of block A, volume of block A, when we're dealing with density. So jot down, make a list of the variables, their symbols, and also what are you looking for? Usually there's a question there. What's the density? Or which density is larger? So density would have a question mark after it. So read the problem. Now, something they left off there that I do, and I know a lot of physicists do, draw you a picture. If it's appropriate, draw a picture. Remember my ugly little table there with blocks on the table, I tried to draw it just so you get sort of a visual concept as well as just reading it, okay? So if it makes sense, draw a picture. And boy, you'll see some pretty ugly pictures coming out of me. Okay. Now, once you've written jotted down the information they gave, drew your pictures, show relationships and stuff. In showing those relationships, sometimes look at the numbers you have and what had better follow those numbers. What follows a number? The unit. Be sure you put the units down there. And when you look at those, see how they relate to each other. And that is suggestive of your equations. Okay? So it says, inspect the list of variables in the unknown. Identify the equation that expresses a relationship between those variables. A list of equations discussed in each chapter is found at the end of the chapter. So take a look at it. So write the equation on, and they say on the left side of the paper, right side of the paper. I don't care where you write it, just write it somewhere. Okay, then step 3, try to solve that equation. Now, they do things one way, and sometimes I see students doing them pretty much enough. I don't care which way you do it. I like to call them plug and chug or chug and plug. I don't care which. Most students like to plug and chug, it seems like. The book sort of likes to chug and plug. And what I mean by that, for instance, let's go back here. Goodness gracious, I thought it would be some, here, okay? Here is a relationship we know about density, mass, and volume, right? Well, what if they gave you a problem that gave you the density and the mass and asked you for the volume? How would you do that? You know the density, you know the mass, how would you get volume? Okay, now here's, I'm making the illustration here, so I'm going to try to remember. It seems like one of those we did was a 2.70 grams per cubic centimeter, okay? Say again? I can't hear you. Okay, very good. All right, now, she is illustrating what I call chug and plug, okay, is you're looking for volume, so I would do it, I know what you're saying, let's multiply both sides of the equation by volume, right? That takes it out here and puts it over there. I want to isolate the volume, that's what I'm looking for, so now I'll divide both sides by density. That wipes them out here, and that gives you a new equation. Volume is equal to mass over density. Now I plug in the numbers. Now I see students a lot of time taking the original thing, plugging in the numbers, and then rearranging them together. Either way works, okay? You do what you're most comfortable with. Frankly, it's a little less writing doing it this way because you only have to enter those numbers and units once, rather than having to carry them all the way through the problem, okay? So mess with the letters, they're easy, and then plug in the numbers, okay? Yeah, that's exactly right. You do mass divided by volume. You do the same thing with density, velocity, distance, velocity, and time, right? You can move those around. In fact, I'll go and show you this now. We'll use it many times in the future. I don't know, y'all probably have already done it. I bet you did it with electricity, but I'm not sure, I'm guessing. Let's take this relationship we had here. Rho is equal to M over V. You can write those in a triangle or circle. I don't care which. I kind of like triangles better. Draw you a triangle and find what's over and under, okay? And split that triangle kind of in half. It's not quite half. But split it horizontally that way. The thing that's on top, put on top. The other two things, put on the bottom, okay? There's a V there, okay? This is a dividing line. The horizontal is a dividing line. This is a multiplication line, okay? I don't know, have y'all seen this before? I thought you probably had. When you're looking for density, cover this. It's mass divided by volume. There it is. If you're looking for volume, which we said here, that's mass divided by density, which is exactly what you said. If you're looking for mass, what's it? Density times volume. So there you can do any of these relationships that's done by a ratio. You can set it up this way. Other people like circles better. Y'all like circles better? I don't care. You could do the circle, do a semicircle, then do the bottom half divided. That's the multiplication line. That's the dividing line. Mass, density, volume. Same thing. It's just whether you like circles or triangles. You could. I bet you did it with Ohm's law, didn't you?
Pretty sure.
Huh?
I'm thinking it works.
Okay. You can use lots of things with it. Lots of things. So, what's that? Distance, time, and velocity works perfectly in that. Distance on top, time and velocity on the bottom. Exactly. All right, good deal. Okay. Sorry. Okay. We weren't quite there yet. But, and since they have it here, I wasn't going to mention it, but since they do, here is a circle on this page, okay? I'm sort of interrupting things again. And tell me a few things about a circle.
Round.
It's round, very good. Okay, that's what makes it a circle. What are some dimensions you know about circles?
360-degree radius.
Okay.
Diameter.
All right, say that again.
Circumference, diameter, radius.
Okay, circumference, diameter, and radius. What is your circumference? Distance around the circle. The radius is from the center to any place on the circle, and the diameter is,
Completely across the circle.
yes, the longest line across the circle. Okay? How are two of those related to each other real quickly?
Circumference and height.
Yeah. Say again?
Radius and diameter.
Okay, radius and diameter, how are they related?
With the radius half the diameter.
Is half the diameter, or the diameter is twice the radius. Very good. Now, are circumference and diameter related in any way?
Yes.
Yes, they are. You remember what way? By a ratio. Anyone know what that constant proportionality is there? We'll do it in lab. It's in the book, but we'll do it in lab. Anyone happen to know? We'll be there. We'll get there. Okay. Since the picture was there, I thought I'd go on and mention it. And they do mention it in the book too, so if you got the book, you can see it. All right, so then we went about solving the equation, and like I said, they like to solve it numerically. Some people call that literal equations, literal meaning with letters, and then plug in the numbers, or you could plug in the numbers first and then solve for the one variable letter you don't know, okay? Plug and chug or chug and plug. Now, I think way before you did that, they put it as step 4, not good, okay? When you have listed all those numbers when you're reading the problem, okay, you put the units, didn't you? Yes. And what if your units are all screwed up? What if you have inches in one place and meters in some place and miles per hour someplace, kilometers per second? Yeah. You got to make sure you get all your units consistent. They list that as step 4. Malarkey. Put that right at step 2. After you've written down the list, if they're not in the same units, you choose the units you want, get all of them into those units. Okay? Why wait to step 4? That's crazy. Okay, now do y'all know how to convert units nicely?
The chart way.
The what?
I know the way to do it on the chart.
Okay, on the chart? Okay. This may be what you're talking about. Let's see if it is. Okay. What I think I'm going to do is, y'all give me some dimension quantity. Something that has dimensions in it that you might want to change. What is wrong with this thing? Okay. Okay, got it. What is a quantity that you might run into one day? Second? Meters. Okay, give me a number with it. How many meters? 10 meters? Okay, let's say goodness gracious, this thing drives me nuts. Okay, let's try it again. 10 meters. And let's say, what are we trying to get this to? What units would you like to have it in? Feet, okay? Let's go blank feet, okay? Now, this is how I do unit conversions. If you have a way you like better and it works, go for it. What I do is put 2 blanks here, okay? Now, one of these blanks is for numbers and one of them is for units. And my rule is always put the units in their place, okay? So if this is going to be units, I'm going to have meters on one, either top or bottom, and feet on the other. Which goes where? Which on the bottom? Okay, say something, I'll see. Feet on the bottom? Okay, let's try that. Okay, let's put feet on the bottom and meters on top. When you were to multiply those, what do you get? Meters times meters is meters squared per foot. Is that going to be a foot? No. Okay, so let's not do it that way. Okay? So what's another way we could have tried? Say again? Okay, let's put feet on top and meters on it, though we're used to having feet on the bottom, but never mind, that's something else. Now we see that sure enough, the meters are going to cancel out, and you're left with feet. So that's going to guide your thing. Now, for those who have the big books, the little books are cheaper, but the bad news about the little books, they don't have the conversion factors in the front. But anything you need, we can get for you. If I'll give you or whatever. I can make copies of this if you need it. Okay? But most of the time, your chapter will have it. Here's the conversion factors, and it says length. See if you can find one of these that relates meters to feet. Anyone got a book like this? Say again? You don't have a book. So I'll read out of my book. Okay? It says that 1 meter, so match the numbers with the units, 1 meter is equal to 3.281. Yeah, 281 feet. Okay. So what you do is multiply numerators, divide by the denominator. That's a pretty easy one to do. That'd be 32.81 feet because the meters canceled out. Right? All right. And you can do all sorts of conversions that way. Oh, I didn't write down the answer. What's that again? Okay.
You see where the one that you're reading from? It said equals 39.4 inches.
Okay. What if that's what you had? That's a really good point. Let's say we had 10 meters, and the only conversion you could get handily was meters to inches, right? So therefore, which would you put where? Always put the units in their place. Meter, say, inches on top, and meters on the bottom, and there was your conversion. You just said what? 39.4 inches, that goes on top. 39.4 inches is 1 meter. So you put that on the bottom. But that's not going to get you feet. That will get rid of your meters, but it will not give you feet. Did you finish? Good deal. Thank you. Okay. That won't give you feet. So what do we do next? Okay. You do another 2 blanks here, and that will get you to feet. What do we put where? Inch. You always put the units in the place. Inches on bottom, feet on top. And how many feet in an inch or how many inches in a foot? Always match the numbers with the units. 12 inches, 1 foot. Then the inches cancel out. And again, multiply by your numerators, divide by your denominator. So this will be 394 up here, divided by 12. If someone has a calculator, do that. 394 divided by 12. Up here we got 32.81. What do you get there? Say again? That's 3.28. Okay? I think it's a 32.8. Okay, it's 10 times. Did you multiply by 10? That's it. Okay, 10 times 39. Yeah, if you divide this by that, you get 3.28. Multiply by 10, you get. Look at that.
So that 10 didn't cancel out?
No, the 10 doesn't cancel out. Only the units cancel out. You keep the numbers.
Okay.
Okay, if so, yeah, I'll loan you $10, and then I'll cancel that out, and then you owe me. No, we'll not do that. Okay.
But it's still 3. So it just takes the decimal away and you divide it by 12.
Yeah, well, yeah.
32.
Yeah.
83. Yes, sir.
32.83, actually, and that was 32.81. Now, that's showing something else. And this book is usually pretty good about that. Here's the issue. How many digits do you have here? 2 at most. Sometimes a 0, you're not sure whether that's significant or not. So therefore, even though this is 4 digits, you only got 2 coming in. You really should only have 2 coming out. So this really should be approximately 33 feet. Same thing down here, 2 going in, 3 here, still you limit it here, 2 here. Now, this inches to feet, that's exact. So you could put 12.00000 because there's exactly 12 inches. They're not exactly 12 inches and 39.4 inches in a meter. That's approximate. This is approximate. But it's good to 4 digits. That's good to 3 digits. This is good to as many digits as you want, but you still are limited by this. That's only got 2 digits, so this answer should also be approximately 33 feet. So you see, you don't argue over whether this is 0.81 or this is 0.83 or 0.8. Those are insignificant. Okay? It's about 33 feet. You only got 2 digits coming in, you can only get 2 digits coming out. That makes any sense. The rest of them are made up. Okay. All right. Okay. Is that enough on unit conversions? I've got several other examples, but I don't want to bore you with them. You okay with that? You can have multiple things, like you could convert feet per second to miles per hour. You might have several of these in there. When you said whatever you called it, is this what you're talking about? Is this pretty much what you did? Okay. It's a pretty. Oh, you did? Okay, good. That, to me, this way makes sense to me. But if you got a way that makes better sense to you, use it. You're fine. Okay. As long as it's right. Okay. That's the key. All right. So that number there, step 4, convert unlike units. Get that done early on. Don't wait till step 4. Okay. Now you're ready to substitute numbers. Okay. Yeah, that'd be okay too. And notice how we do it here. You either look it up in a table or things you already know. You know there's 16 ounces in a pound. You know there's 8 ounces in a cup. You know some things, so use the ones that you know. Okay? And substitute the numbers. If you solve for your variable, then plug in the numbers. If you did literal equation. Do the indicated mathematical operation. Boy, they drag this out, don't they? Divide, multiply, subtract, whatever. Now ask yourself if the number seems reasonable. 10 meters. Does that sound reasonable to be 33 feet approximately? Yeah, a meter is just a little bit longer than a... What was this? A yard, and this is a meter. So it's just a little bit more than a meter. How long would 10 yards be? Okay, yeah, but how many feet would it be? 30 feet. So this is a little bit longer than 30 feet. 33 feet. Yeah, that makes sense, doesn't it? Okay? I think of football fields all the time, okay? If so many yards, does that make sense, okay? Okay. Oh, I love their little step 8, don't you? Draw a box around your answer. I don't care. You can put a circle around it. You can put an arrow and say, there it is. I don't care what you do. Just make sure I can see what your answer is. They draw little boxes, so that's good. I'm proud of them. Okay. Let's do the problem they're doing. For an example problem, let's clear this stuff out of the way here. Okay. In the previous section, they talked about a problem. Here's what it was. They said the volume of a tank is equal to the time that it took to fill the tank times some constant. That's a proportionality, a direct proportionality. The longer you pump into the tank, the bigger the volume that you got in there, right? Okay. So that's the proportion they have. Now, what is their constant there? Their constant is your flow rate. And their flow rate happened to be 40 liters per minute. They're using that, aren't they? So this was 40 liters per minute. So their formula was volume to fill the tank is equal to 40 liters per minute times whatever time you were pumping. Okay? So there's your formula. It says, use that formula to predict how long it will take to fill an empty 80-liter tank. How long to fill an 80-liter tank. Okay, that's the problem. You got your formula, you got your flow rate. The question is how long to fill an 80-liter tank. What are you looking for? Where's your question? How long? Now, sometimes when you read a problem that says how long, that means how long. Is that what this one's meaning? No, they're meaning how long. Okay, you have to interpret. That's time. So what are you looking for? What's your unknown here? Time. That's the unknown. 80-liter tank. What in the world does that represent? Volume. So your volume is 80 liters. Very good. Now notice here they put capital L for liter. That's not named after anybody. That wasn't named after Joe Liter. You know? Why did they put capital L for liter? I thought we used little l. Well, let me do that. Let me write that as 80 little l. What's wrong with that picture?
Looks like one.
Oh, that looks like a 1. You might think that's 801 something. So therefore, for liters, we put capital L, just so we can distinguish it from 801. Okay, yeah, that's 80 liters. Okay, dumb question. Okay, how are we going to answer our question? How long?
Plug it in.
Okay, he likes to plug and chug. So what do we plug in? 80 liters is equal to 40 liters per minute times t minutes. We'll leave off the units there. Okay? How are we going to solve that?
Put 80 over 4.
Exactly. Divide both sides by 40 liters per minute. I know it gets a pain to drag all these units around, but it's worth it. 40 liters per minute. Now notice here, of course, I know how many times 40 will go into 80. Don't you? 2. The liters are going to cancel out. And what you're left with is 1 over minute. Okay, this should be a minute. Okay, what's 1 over a minute? How do you divide fractional forms? You could write that as 1 divided by 1 over a minute. Just treat them like they're numbers. How do you divide a fraction? Invert and multiply. So it's 1 times minute over 1. And sure enough, that unit is going to be minutes. Okay? Move that up there and it becomes a minute, because it's 1 over a 1 over, okay? So your time is 2 minutes, okay? Does that make sense? Is that reasonable? You got a 40 liter per minute time rate? Yeah, in 2 minutes it's going to be full. That makes perfect sense, okay? And they drew a little box around their answer. I didn't. Shame on me, okay? Here's my little box, okay? I don't care, you know. Just make sure I can see it. Okay.
So on the plug, okay. So the way to do that is
Plug and chug?
Plug and chug.
Okay, the other way would be chug and plug. When you had your formula here, I know I had it somewhere there. There it is. V is equal to KT. Since we're looking for time, divide both sides by K. Okay, the K's go out, and that leaves you T is equal to V. Well, V is now plug. You chug, now you plug, divided by K, which was 40 liters per minute. And that way I didn't have to carry around those units as long. So
That's the easiest.
That, I think it's easier, but a lot of people like to plug in the numbers as soon as they got it. It works. It's just a little. See, I have a theory about people in math and science. My theory is I think they've got to be a little lazy to be good at it. Why? Because they're always finding the easiest way to do the problem. Now, are any of you qualify? No, you're all hard workers. Well, you can still do it, but if you're a little lazy, you got an edge over these other guys. Okay. All right. All right. Now, they go through gory detail over finding all that stuff. I think we've already done it. Let's do another example problem, if it's okay. Problems are important. That's where that's what you deal with every day. You know, how long is it going to take me to fill this tank? You know, mercury is a liquid metal with a mass density. What's symbol for mass density? Say again? Okay, no. That symbol, mass density. Funny little symbol. Looks like a P. Rho. No, okay, never mind. Rho is equal to 13, and this is for mercury. Mercury is Hg. Okay, you don't need to know that, but I'm putting it. 13.6 grams per cubic centimeter. Does that sound like a good unit for density? Yes. Mass per unit volume. Mass in grams, volume in cubic centimeter. Yes. Okay. The question is, what is the mass of 10.0 cubic centimeters of mercury? I'm lazy, so I put Hg. Okay? By the way, we're going to be doing chemistry at the end, so might as well get used to these simple chemical symbols. Okay? How would you say we're going to solve this problem?
We're looking for mass.
We're looking for mass. You got it. So this is the unknown. M is the unknown here. Good. You already know what 13 point. Say again.
Cubic. I mean, how do you say that?
The cubic centimeters. 10 cubic centimeters. Is that what you're saying?
Yeah.
What is that?
Of mercury.
Oh, okay. That's your rho. That's your density of mercury. That's the density. That's the mass density. Okay, as opposed to weight density, which you use here in the U.S. Okay. How about that 10 centimeters cube? We haven't said anything about that. Yeah, but what is it? What does that represent? That's your volume. You're right. That's the volume. That's the volume of your mercury. Okay? Now, you have density, mass, and volume. Do you have any relationship that ties those together?
Yes.
You sure should.
Yes.
I hope you do next time. What is it?
The cubic.
Okay, deal with the symbols.
The C.
What's that equation? Yeah.
Cubic meter.
Okay, don't worry with units yet. We're going to get there. What's the equation? Symbolic equation. We've done it several times. It's rho is equal to m over v. That's it. That's your mass density. Density equal mass divided by volume. Got it? Okay? Now, how do you want to solve this? What are we looking for?
Volume.
No, you told me it was
Mass.
mass. Okay? So which are you going to solve for? Solve for the mass. And how do you do that? What's messing up the mass? It's divided by v. So how do you undo a division? Multiply. Okay? So let's multiply both sides of the equation by v. Okay? And what happens to v's here? They go away, leaving you a naked mass. Okay? M is equal to, I'm going to rearrange the order, rho v. Okay? Or you could have done your little triangle or your circle and put the m on top, the rho down here, the v down here. This is multiplication. And you see you're looking for mass, and that's rho times v. There it is. right there.
Okay, so Dr. Fowler.
Yeah.
So you said do your set up your equation first.
Yeah.
Okay.
Yeah. Well, once you know what you've got given and looking for, find an equation that makes sense. That was the equation we knew. Rearrange it this way. Now you have chug, let's plug. M, that's what you're looking for, is equal to
13.6.
yeah, 13.6. That's just a number. Grams. Not just grams. Per cubic centimeter. Get them all in there. Okay. Times, because you're multiplying by volume. What's your volume? 10.0 cubic centimeters. And guess what? The cubic centimeters go out. They've been dating. No, I'm just kidding. Okay. And what does this give you? 136. 136 grams. That a good unit for mass? It's a very good unit for mass.
Now, why did you?
Because you multiply 13.6 times 10. And you lose your decimal one place. Yeah, calculators slow you down a little bit, but yeah. Okay. No, I'm just kidding. No, use your calculator. It'll work.
If you know how to plug it in and set it up, you should be good.
Yeah. Now.
No, you said don't plug and chug.
No, it doesn't matter which way you do, whichever makes
Don't
the
you know
most
how to
sense.
set it up?
Yeah. Set it up and then carry it out. Okay, now let's take a look. How many significant digits did we have here?
13.
How many digits?
3.
3. How many digits here? 3, because that 0.0 means you're to the nearest tenth of the cubic centimeter. So that is significant. So you better write this answer in 3 significant digits. If that was just a 10 without a 0.0 on it, you'd round this to 140. Because only 2 in it, you can only get 2 out. Okay? Okay, good deal. Let's see what they got. They got 136 grams. Good for them, and they put a little box around theirs. Okay, good deal. All right. There's a little box. Okay, good deal. Okay. Now I think finally we're ready for the nature of science. Okay? Now this is sort of interesting how this book refers to it. This author says science didn't begin until about 300 years ago. I have a little problem with that. Science has always been there. We just didn't understand it maybe until about 300 years ago. But in reality, I mean, there's a part of it that's right. Because until you organized it, it was all just sort of out there. Now, some people consider Aristotle a great scientist. He was a great observer, okay? The ancient natural philosophers, that's what they called themselves, not really scientists. They only thought about things. And we're going to be talking about Aristotle a lot in the course because Galileo, particularly, took on Aristotle, even though they lived thousands of years apart, and said, look, all this stuff that everybody believed just because Aristotle said it ain't necessarily true, okay? And actually, we say science began with these two characters. Galileo from Italy, Galileo, or something like that, funny name, and Isaac Newton. Galileo from Italy, Newton from England. And the really unusual thing here, I think, to me, this is just ironic. Ironic here is that the very year that Galileo died, that same year on Christmas Day, Newton was born. And, I mean, and so they never met. Obviously, even if they had, he would have been an old man and a little baby. That was but it's sort of like they did a tag team on the way out. And it's never mind. I didn't say that. Okay, so they began, and what Galileo did, the ancient philosophers just thought about issues. I'll just give you an example. Good old Aristotle made this statement. Heavier objects fall faster than lighter objects. And that seems reasonable, doesn't it? Okay? Galileo said, Let's think about that a minute. Let's do some measurements and see. Okay, do you think heavier objects do fall faster than lighter objects? Sort of hate to destroy these two, but I made these announcements long enough. Would you say these two objects weigh about the same amount? Approximately. Yeah, both of them pieces of paper, they weigh about the same amount. So would they fall about the same? They should fall about the same. Okay, I heard you say that. Okay, now I'm going to drop them. They weigh about the same, right?
Don't matter, surface area.
Say again?
Surface
Oh,
area.
it's not the weight. No, it's the surface area. And some other things too. They weighed the same, but they fell at different rates, didn't they? So Aristotle had never thought about that. He had never tried that. He never tested that. That's what Galileo did. Additional component here is understanding based upon experimental evidence. He said, let's make some experiments. Let's take some measurements and see if this is indeed true. And he found, no, everything falls, if you take other things into account, about the same rate. And we'll see this in lab. Not this coming lab, the next lab. Okay? So here's a scientific method, and again, you'll see this in so many books, and they may have it in slightly different order. This is about what's going on. We do what the ancient philosophers did. We observe. We look. Okay? Observe some aspect of nature. Okay? And then Aristotle did this too. He proposed an explanation. He said it looks like lighter objects don't fall as fast as heavier objects, so I'll say it. So he just did that. He stopped pretty much right there. Or maybe he went one more step and said, well, therefore if I have a rock here and a ping pong ball here, though they probably didn't have ping pong back then, let's see it. If predict what's going to happen here. And here's where he quit. Okay, he may not have even gotten that far. He just said, this is what I observed, this is what I think it is, therefore, and everybody said, Aristotle said it, we believe it, we believe it. And no one questioned Aristotle for about 2,000 years or so. I mean, it was a long, long time, okay? Galileo came along and said, well, let's test those predictions with experiments and make some observations, more observations. Well, he did that, and then he said, that doesn't fit. So maybe this does. Modified the explanation, then try it again, okay? And then keep doing that until you say, this looks like it's pretty close to true. Don't know that it's absolute, but everything we can measure seems to indicate this is true. Aristotle didn't do that. That's what Galileo and later Isaac Newton did. Newton took things Galileo had found and really expanded them and did them big time. So here's an example, and this is sort of a strange one to do here. We'll run into this again when we get to chemistry. What are atoms made of? Okay. Interesting question. And way back even at Newton's time, nobody knew this. Y'all know it now. But what we know now is it's negative electrons floating around a positive nucleus. Okay? Now, it's a really weird setup, okay? Because that positive nucleus, nuclei is plural for that, but nucleus, is extraordinarily tiny. I mean, incredibly tiny. And the electrons are flying around a much bigger volume around that nucleus. But the nucleus contains, as they're going to say here, protons and neutrons. Well, protons and neutrons are really very massive, whereas the electrons have just the tiniest amount of mass, about 1/10,000th of the mass of a proton or of a neutron. I mean, tiny, almost no mass. So here you have, for an atom, almost the entire mass of that atom compressed into some very incredibly small little space, and then these tiny, tiny little electrons flying around all around it. Now, I can remember my brother coming home from his first year at Georgia Tech, maybe his second year. Yeah, second year, I believe it was, when he took physics. And he had a really good physics professor. He really liked him a lot. And he came home and said, most of everything is nothing. You know, I thought, what? Because most of any material, the material itself is concentrated into a tiny little nucleus with these incredibly small electrons taking up almost the whole volume. So in between that is absolutely nothing. Empty space, really. Nothing in there, okay? So most of everything is nothing, okay? Pretty incredible. Even something like lead, most of lead is nothing. That the solid part, the heavy part is located in nuclei, and around that are electrons, but most of the space in between there is empty. So, incredible. Negative electrons orbiting positive nucleus. Now, if you collide two atoms, you produce some free electrons and some blank nuclei without any electrons around them, or with fewer electrons. Okay? So that would be the experiment to see, yeah, I can break these apart. Colliding two atoms yields electrons. Those are the free electrons. If you collide them anymore, you could actually split the protons from the neutrons in the nucleus. Boy, you've got an atomic reaction going on there. So atoms are made out of electrons, incredibly tiny little electrons, orbiting the nuclei made up of protons and neutrons. And then, well, let's see. Let's collide them at larger energies and see what we get. And as they keep doing this, they found other incredibly tiny little particles that are also in those nuclei. We're not going to go there, but they have found them. So that's sort of a weird example to give at this point in the book, but that's how the scientific... Now, this took centuries for them to get the technology to do all this, but they certainly have done it. So anyway, it's a weird example, but it's a very good example of scientific method. Now, most of the rest of this chapter is blah, 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 okay? Some of the general scientific activities, just like those ancient Greeks, we make observations. Careful observations, okay? And actually, Newton himself was an alchemist, and he recorded just about everything he observed. He was incredibly precise. In fact, many of them were. Collect those observations, start developing explanations that explain those observations, but then once you develop those explanations, you've got to test them. That's what the Greeks didn't do. That's what Galileo and Newton and everybody since then has done. Test those explanations, see if they work. If they do, fine. If they don't, develop other explanations that do better. Now, we do this in all sorts of things today. My wife is a researcher at UAB. She's an epidemiologist. She studies diseases. One that she studies is called cytomegalovirus. It's a herpes virus that if you were to catch it, you might feel a little bit like a very mild case of the flu and you'd be over it, no sweat. But if a woman happens to be exposed to it when she's pregnant, she may not feel sick or anything, but if that virus makes its way into the uterus and infects the baby, then the baby could have no outcome, or it could have some mild outcomes, or it could have some very serious outcomes. So she's been studying this most of her career at UAB, and they found out that a lot of hearing loss is related to cytomegalovirus, especially kids that can't hear and they don't know why. They think maybe they were just born that way. No, most of it's because they were infected with CMV when they were in utero, okay? Yeah. And what's more, y'all have been hearing about Zika virus? Okay, what is the bad thing about Zika virus?
They say don't get pregnant.
Okay, yeah, pregnant women will have sometimes children with small heads, microencephaly, and they usually don't live very long. What's that?
I'm just saying they've already done the experiment.
Well, they mostly observations.
I mean, there's
For
no
some,
observation.
but mostly observations so far. But guess what? CMV causes more microencephaly than Zika does. And yet everybody's up in arms about Zika, and cytomegalovirus has been known about for years. But people just don't think about it. And they don't tell women when they're pregnant, here's things you need to do to make sure your child doesn't catch it. Yeah. So I don't know, I mean, I'm off on a different subject there. But you see, so what she's been doing is developing explanations, testing them. Right now, the latest proposal she's made, they think there may be some association with autism and cytomegalovirus infection. So they're investigating. They've made some observations. They have developed a few explanations. They're in the process of testing them. That's the next project. She's trying to get it funded. She may or may not get it funded. If she doesn't, she's not going to be able to. So let's look at a few of the methods that we do. Explanations and investigations. What they call a hypothesis is that first tentative explanation for some observation. For instance, they had observed enough things, they said, you know, it looks like to me that cytomegalovirus may affect hearing loss in young children. Okay? That was their first tentative explanation. So they did a bunch of it, they designed experiments to test that. They tried to recreate events or occurrences to test hypotheses. Now, when you're dealing with humans, you can't do the same type of stuff you do in other parts of science. You can't go out and say, okay, lady, you're about to get pregnant. You would like to get infected with CMV, you know, to see what it does to your child. No, we don't do that, okay? What they do is they do it retrospectively. What she did was, at UAB Hospital, and not just her, others have, okay, they tested newborns to see if they were CMV positive or negative. If they were positive, then they tried to find a newborn born close to the same day, of the same gender, if it was male, another male, and that didn't have CMV when they were born. Okay? And they did literally thousands of comparisons like this, put them in a database, you know, stuff, and did the thing. Tried to control for as much as they could. Socioeconomic status, they controlled for race, they controlled for, you know, as many things as they could. And then they measured and said, yep, those that were born with CMV were 3.5 times more likely to have hearing loss than those that were born without CMV. So yeah, that must be possible. So they created the experiment, tried to recreate the event, make the comparison. The control was the kids that didn't have CMV. The factors that they were doing, they tried to control for race, for age, for gender, for socioeconomic status, for all the things they could think of. And the control group was those who didn't have it. The experimental group were those that did. Okay? And then they said, can we see any difference? And she looked at the numbers. They're called odds ratios. Sure enough, came out a lot more. What they're proposing now, do that with autism. Okay? The odds are, the thing is, they're going to have more subjects, okay, because autism isn't as common as hearing loss, generally. So they're going to do that. There's just, I mean, but this is happening all over in science everywhere. I mean, age research, that's basically the type of thing they do. Come up with an idea, design an experiment, have controls and cases, experimental groups, see if they can see any difference. Okay? Now, this author is kind of big on what he calls pseudoscience. Does anyone know what this prefix pseudo means? Fake. Okay? Not true. Okay? A pseudonym, anyone know what that is? Second?
A word that's
Okay, it's similar to that, but it's not synonym. Pseudonym. Pseudo is a fake name. Let's see, I'm trying to think. You know who Samuel Clemens was?
No.
He was an author, but he didn't use the name when he signed his books. Samuel Clemens, he used the name Mark Twain. Exactly. Mark Twain was a pseudonym, fake name, false name for him. I don't know why he did that. He just thought it was a cool name because that was how deep in the water you were. What's that?
It was the name of one of the boats he was on when he was a river captain.
Yeah, what that was named for was when you were measuring the depth and you were coming up on shore, you worried if you got more than Mark Twain. You know, that was when you were getting close to going to the ground. Okay, so that's where it came from. Others in past, A.A. Milne, I think it was, wrote children's books, but he didn't want to use his whole real name. I think he was a doctor, and he thought children's books were really silly, so he wrote under a different name. Sometimes it happened that women couldn't get published unless they used a man's name, and that happened quite often. Second,
There's 3 sisters that did that. I don't remember their names.
was that the Bronte sisters?
Yeah, I was gonna say.
It may have been. I didn't know they used pseudonyms, but yeah. So that's what pseudoscience is: false science, fake science. Unfortunately, guys, gals, the internet is full of pseudoscience.
Wow.
People make any kind of statement they want to. They're sometimes misleading, often absurd claims of scientific results that just aren't there. I remember when I was teaching the other course of this, the 111 astronomy side, they were certain that this meteorite that had landed in Brazil or Bolivia or somewhere in South America was making people sick, you know, and they thought it was an alien germ invasion or something. But then when they went to check it, there was no foundation. People in that area had very poor nutrition. No one paid attention to them. They had been sick their whole lives, you know. And, you know, so, all right. Here are some of the tests. Academic or scientific background of the claimant. If you got somebody who was a shoe salesman out there claiming that he's discovered the cure for cancer, he may have, but the odds are maybe not, okay? I think he's going to have a lot of biology, a lot of biochemistry, and a lot of other things before he can make that claim. Secondly, a history of review by scientific peers. That means other people who know what they're doing. My wife, I said, was an epidemiologist. She gets bombarded because she's done some pretty good work. She gets bombarded by, can you review this paper? Can you review this paper? And she said, if I did all those, I wouldn't have time to do my own research. So I've had to tell them sometimes, no, sorry, but here's somebody I think has time to do it, you know.
Right.
So, but she does review quite a few. In fact, when we were at a wedding earlier this month, she had to take her stuff with her because she was already a week late in reviewing the paper. So yeah, review by scientific peers. Participation in scientific institutions and organizations. You know, the people, Lone Rangers don't do very much in science. They collaborate. Even Galileo and Newton, even though they didn't know each other, Newton read Galileo's work and he based his stuff on what Galileo had found. They've got to really participate and work together. Claim published in peer-reviewed articles, this is almost the same type thing. In other words, before something gets published, it usually is reviewed by 2 or 3 people who knew what they're talking about, read through it and say, yeah, I'm not too certain about this method here, need to check on it. And sometimes it takes another year or so before, okay, yeah, it looks like you got everything, you know, let's publish it. Otherwise, we'll have people getting sick in South America because of the meteorite landing, which it really wasn't, okay? So you have to be careful. That's pseudoscience. Now let's go to real science. Now, some of this stuff differs only by a little bit, okay? For instance, a law versus a principle. Some people call some things laws, others call them principles. A law is an important relationship observed to occur time after time after time. You throw a ball into the air, it comes back down. You throw it into the air, it comes back down. We call that the law of gravity. It always works, okay? You can't throw it up unless it gets stuck on a ceiling or something. Yeah, no, it's going to come back down. That's a law, okay? It's usually just descriptive in nature. You throw something up, it falls back down. You're just describing it. Here, this isn't me. This is someone whose last name was Charles. Charles's law is the relationship between temperature and pressure in gases. Okay? Y'all know what that relationship is?
Temperature and pressure in gases.
Yeah. How do they relate to each other? If the temperature goes up, the pressure goes up for sure. That's why you don't decide whether to add or take air out of your tires if you've been driving in the middle of summer for the last 200 miles and your tires are really hot. Oh, these are overinflated. Let me take some air out. No, don't do that. That's not the best time to do it. I can remember when I was living in Nebraska working on my PhD, there was a lady in our church, she and her husband were divorced, he was living way another part of the state, and her son was, young teenager, and she said he really needs to be around some men, not just around me, and so she asked people in the church if we could. I was single, I said, not me. But then we got on the same church softball team, and he and I just hit it off, so I started doing things for him, so went over one Sunday evening, and he had been shooting baskets out in his yard. It was cold in Nebraska, by the way, really cold in Nebraska. He had forgotten to take the basketball in. And so that Sunday afternoon, it was still pretty cold, and we went out to shoot, some hoops, and the ball, he said, oh, the ball's flat. I must have punctured it. I said, no, Matt, wait a minute. Take it inside, let it sit there for a while. We can do something else, and then go pick it up later. He said, what? And so anyway, we did it. And about 30 minutes later, I said, go check your basketball. And came back. It's full. Okay. Charles's law, not mine. If the temperature goes down, the pressure goes down. Temperature goes up, pressure goes up. That's a law. It always happens. Pretty much descriptive in nature. Now, principles, on the other hand, they're also descriptive, but they're a little more specific than the laws. A little bit. That's why I say some things are called laws, sometimes principles. You have to decide. The difference is largely one of extent. Do I want to call this a principle or a law? I don't know. Not always a clear distinction. So some people call Archimedes' principle regarding objects, fluids, and buoyancy, that kind of stuff, a principle. Other people call it the law of buoyancy. Which way you want to call it. Here's an example of one. Let's go back to this piece of paper that y'all like so much. I want y'all to make some predictions and observations. Prediction. What's going to happen if I blow underneath this piece of paper? You think it's going to rise? Let's see. Sure enough, it did. Now, what if I blow over the top of the paper? What's it going to do?
Go
Not
down.
much anything? It rose. How in the world did that happen? Huh? Okay?
Just over musician.
Okay. Have y'all ever flown in a plane? Okay, you have. Aren't you glad it flew? How much did it weigh, you think? Just a few ounces? Several tons, exactly. How did that ton plane fly? Well, a guy named Bernoulli, he was in a family of very famous mathematicians. He came up with Bernoulli's principle. And what he said, the velocity of a fluids are either gases or liquids, as the velocity increases, the pressure decreases. And y'all use this all the time, I bet. Okay? At least in the old days you did. How did you get gas into a carburetor in the old days? Before fuel pumps. Oh, way before your time.
Before fuel pumps.
No, before fuel pump. Say again? Oh, that's into the tank. I mean, into the thing. A carburetor. How did a carburetor work? It blew air rapidly across a material. It sucked up the fuel and it went in. Fuel pumps are a bit more precise and you get a better mix. But in the old days, that's what carburation was that. Have you ever used those spray things to wash windows on a house or something like that? You just screw it in the bottom, the water goes over the top, but it sucks up the soap. Okay? That's Bernoulli's effect. Usually that's called the principle. Bernoulli's principle, like Archimedes' principle. They're all over the place. Usually a little more specific than the laws. Okay? Now, we have other things like theories and models. Okay? I remember way back several slides ago, we had hypothesis. That's your first general idea that you're going to test and stuff. And if you keep testing these hypotheses over and over again, and you refine them and correct them and, get them a little bit better every time, after a while, it seems almost always to work based on broadly based on a set of working hypotheses, based on considerable experimental results, supports, then it forms the framework for thought and experiment to do the next one. But guess what? As long as it's a theory, you're not absolutely certain if it's done, you've got to keep testing, okay? Anyone think of a very famous theory that everybody argues about?
Relativity.
Say again?
Relativity.
I can't hear you.
She said relativity.
Relativity. Yeah, that would be a theory. And that's a rather obscure theory too, but more and more evidence has come up showing that it looks like it's true. Yeah, that's a really good one. Who came up with that? Einstein, Albert Einstein. And for a while people said, well, since it was Einstein, no one wanted to question too much, but they said, can this be true, But more and more, it seems like it is. He also came up with a whole thing about how gravity works. And no one was certain whether that was true until something happened not too many years ago, and some distant star had a nova or something like that, and we watched it, and sure enough, you could see that gravity was not a force at a distance. There were actually some sort of waves that created gravity. I can't even remember that, but I believe that's it, yeah. Yes. Right. It's just pretty incredible. Those are theories. The one I was thinking of, and this I don't want to get into big arguments here, but the theory of evolution, right? Some people say, that's not a theory, that's fact. No, it isn't fact, because guess what? How many people have gone back and experimented and gone back, like the Big Bang Theory? Can you go back and reproduce that? No, you can't. You just look at the evidence and see, yeah, it looks like maybe this works and maybe not. I mean, there have been many theories out there that held for a long period of time, and then suddenly they got a little bit more advanced in science and said, whoops, it doesn't work anymore. So they had to adjust. Okay? I could give some more examples. Let's move on. Then we have models. These are often collections of theories or ideas intended to represent a whole physical system. Okay? Useful for regimes that are either too small or too vast for just direct observation, like the Big Bang Theory. There's no way we can actually do it, but the model is this. They think, could this have happened when that happened? This. There's several questions that still Big Bang Theory doesn't answer, or things too small. Okay, here's the one I was thinking of here. One model that, remember we did the atomic theory, or we mentioned the atomic model. Okay. One of the early proponents of this was a man named John Dalton. And he didn't know why the things happened, but he noticed that things combine in certain ratios. Okay? For instance, if you have a carbon, only 2 oxygens usually attach themselves to it, making CO2. But if you have carbon and hydrogen, you can have 4 hydrogens around the carbon. Or if you have carbon and oxygen, I already said that, didn't I? Okay. Water, hydrogen and oxygen, 2 hydrogens to 1 oxygen. And he said, well, why would this do? He looked at all these combinations, how they combine. He said, it looks like they're little hooks. And you know what? He knew there probably weren't hooks, but he couldn't think of anything. His model said oxygen has 2 empty hooks, hydrogen has 1 each. They hook like this. Carbon has 4 hooks. So 2 oxygens on 2 and 2 on another, that's carbon dioxide, And he started doing this, and sure enough, the model fit the data. Well, later we found out there were things like electrons. It wasn't really hooks, it was unpaired electrons. So his model worked for probably several decades until people discovered what really was going on. And he would have said, it's probably not hooks, but that's just the best thing I can come up with. Now, sometimes they're physical things like hooks. Other times they're mathematical. there was a Scottish scientist, had to be one of the most brilliant guys that been around. His name was James, it's pronounced Clark, but it's spelled Clerk. James Clerk Maxwell. He was observing, everybody was saying how similar electricity and magnetism, they had things in common, but they seemed very different, but they seemed related. He came up just with his mind and looked at the various theories, the ideas, the measurements and things. He came up with 4 equations. Nowadays they're called Maxwell's equations. He said, what if these would do this and act like this and that? That would explain everything we've seen so far, but it was just a model. Science was still probably almost a century later before we had the technology to actually measure the stuff. Guess what? He hit it on the nose just by thinking through it and observing things and putting them together. He came up with a model that, sure enough, still people use Maxwell's equation. No one's come up with 4 equations any better that I know of. So those models can be mathematical, they could be analogies, they could be physical, they could be anything like that. Here's one model. Dumb question, have you ever seen a rainbow? Okay. Have you ever seen one on a really bright day that you see just a perfect rainbow? Okay. And have you ever noticed what's just a little outside of it? Another rainbow. Okay. And if you've ever noticed those, they always seem like they're about the same relative distance apart. And if you really look carefully, you'll see in that first rainbow the order of the colors, but the second rainbow is always dimmer. Always, always dimmer. That's another thing to observe. But the colors are reversed. So what's the model that could represent that? Okay, here's what it is. Let's see if the model works. Now here's the picture. There's the inner rainbow, bright, yeah, wonderful. But this one out here, now notice here, the violet is on the inside and the red on the outside. But notice this one, you can barely see it, but the red's on the inside and the violet on the outside. Sure enough, every time. And they're almost always about like that. You know, almost always that same separation. This one's always brighter, that one's always dimmer. Those are our observations. What model would make that happen? Okay? Here's somebody's model. Okay, now when do you see rainbows? Second? Just after a rain. Now what's in the air when it's just been raining? Little water droplets. Okay? Have you ever noticed where you see rainbows? You ever see them in the middle of the day? Like noonish?
No, late evening.
Late in the afternoon or evening. There's another observation. And when you've been looking at the rainbow, where's the sun? Behind you every time. So what's going on here? Well, we think the light is coming from the sun, hitting those little, and the water droplets are not perfect spheres, but they're close to it, little spheres of water. And on that first inner rainbow, the sunlight comes in. Now, if it comes in here, it goes right through. If it comes in here, it gets refracted. That's what this is, bent. And when it's bent, it's also separated because you see these different rays of light. White light is made up of different colors, different wavelengths. The red is the longer wavelength. The violet is the shorter wavelength. They get bent slightly differently. And then when they hit the back of the rainbow, the back of the drop of water, at a certain angle, it gets total internal reflection. Anything beyond this, not going to happen. Anything down here, not going to happen. But at this certain angle, you get total internal reflection. When it reflects, they flip over again, believe it or not. And then they come out this side and get bent again, because every time they go through a different medium, they get bent. And they get spread out a little bit further. And this is always that angle that you get that total internal reflection. And it comes out, goes in and comes out, gets bent. That's 42 degrees. So if you were to take the center of this rainbow and with a sextant measure, it's always going to be right at 42 degrees. Now, a fair amount of light comes through that window there and gets bent, and so you get a fair amount of light out. That's why they're fairly bright, relatively speaking. Okay? But then there's a second thing. If the sunlight comes in right at the tip of that, now much less sunlight comes in up there than comes in here. Those raindrops bigger there. Okay? So if it's right near the top or bottom, and this is true, top or bottom, then it actually gets bent and has total internal reflection here, but then it has total internal reflection a second time, and each time gets flipped again, so now the colors are reversed twice. So they're opposite what they were here, but this angle is 51 degrees. And that is always about 9 degrees further out here. So there's our observation. It's always when moisture's in the air, raindrops. The sun has to be behind you. The light's coming in parallel. When it goes through a certain span of this bulb, this thing, 42 degrees after that, you get that reflection. The raindrops in here, no. Raindrops here, no. Raindrops here, that's this little angle, you get a double reflection, and you get that very pale because very little light goes through there. A lot more light goes through here, so this is much brighter than that. Everything fits, including the reversal of colors. That's the model. Are we certain that's what's happening? Pretty sure. May not be exact, but it fits. Everything seems to fit pretty well. Okay? All right. Now they say, I've never seen this, but they say if you're up in a plane and the sun is shining through there, that sometimes you can see the whole circle. I don't know if that's true or not. I just don't know. It doesn't seem to fit this model very well, but maybe it would. I don't know. Okay. Okay. Now, that's the last slide in the chapter. And by the way, I meant to tell you this. I didn't have time to get the PowerPoint slides on Blackboard. Now, you can certainly see them all up through YouTube because I've used every one of them and then talked about it. You hear me talking about it. But I hope to get all the slides done on Blackboard. I may actually, if I can remember to take them to the Birmingham campus tomorrow and do them then. I don't know if I have time, but I'll try. There are a few other things I sort of glossed over here. There's a nice little blurb here, the Science and Society, that's well worth a read here. It's talking about basic versus applied research. This is on my book on page 15, so somewhere thereabout. It's a little green block somewhere top or bottom of the page. It's worth a read, interesting stuff, and it has some questions to think about. I'm not going to probably ask you any of these on the test, but still nice stuff to read. I mean, to think about. Basic versus applied research, and there's tons of examples of this. For instance, James Clerk Maxwell, that was basic research coming up with those equations. How we use those equations? Well, many scientists since then say, hey, since that's true, maybe we can do this or that. And then that's applied research. Same thing through, let's talk about my wife's research with CMV, cytomegalovirus. There's some people out there who are actually studying that virus and studying how it might go through the placenta and interact with the, whether it's primary infections, reinfection, or secondary infections. There's all that basic research going on. She's doing more of the applied research. She uses that basic to say, is this reasonable to think this might happen? So it's a nice little blurb, well worth a read. Okay? Then there's that blurb on pseudosciences. This guy's really big on that. There's Charles's Law, the pressure versus temperature. No, this is not Charles's Law. This is, well, yeah, it is, but it's volume versus temperature here, not pressure. Okay, but those are related. Then there's a picture on the rainbows. Another, and this is in Physical Science 111, which most of you probably won't take, or you might. You know, if the auto mechanics, I know, will only take this one. The others of you could take this other one. And it's based on somebody at some time way in the past looked at a globe and said, you know, it looks like South America could fit in the arm of Africa, you know. And it looks like and they said, I wonder if the continents are really divided and moved. And people at the time said, are you crazy? Continents can't move, they're fixed in place, you know. But guess what happened about 200 or 300 years later? People found out they really are moving. That whole theory of plate tectonics came up. Yeah, they have been moving very, very, very slowly, but they've been around a few billion years. They probably did originate there and move. So there was an example of something that people thought was ludicrous at the time, and now we think, hey, they were probably right. There's many examples of that. All right, now I've said it before, I'll say it again, I'll say it every chapter. Nothing replaces reading the chapter. Not listening to the lectures over and over again, not watching the PowerPoints. Nothing replaces reading the chapter. You're going to get way more from that than you will listening to me. So try to read the chapters. Once you've read them, the summary at the end is a pretty good thing to do. It's sort of like Reader's Digest condensed books. You know, it just takes it down into a small, but try to read the chapters first. Now, just about every chapter has at least one blurb on people behind the science. This is talking about Florence Bascom, which frankly I'd never heard of her before I read this book, okay? And found out she was quite a scientist back before women were supposed to be scientists, you know. She was a geologist, and she did some early stuff. So guess what? If you wanted to write on her, here's an idea, but guess what? This isn't your source. Your source has to be from outside the book. Something in the library, something on the internet, or something like that. You can write on her, but you can't use this. You can use this as the idea of the springboard. Now this has summary of equations. This chapter only gave you one equation. Y'all mentioned several others. We've mentioned several others. We only are responsible for that one. And the key terms, there's a number here. Now unfortunately they list them in alphabetical order, but the good news is they put the page number by it so you can find where they're located. And then, frankly, now, not so much for this chapter test. For the later chapter test, this is going to be a great thing to do, applying the concepts. Multiple choice questions. There are 44 of them here with answers. So I would say, not a bad idea to read through these. You guess your answers, then compare them to the real, then go back and see if you missed any, why you missed them. That's a good way to get a good feel for what's going on in the chapter. Now, in this chapter's test, going to be a few more calculations, not as many multiple choice, because the test bank was really weak in this chapter. So I've made up another one that has a few more calculations on it. So they'll be somewhat useful for this chapter. Later chapters, those will be great. Then there's these questions for thought, and that's exactly what I do. I'll read through them, see if I understand what they're asking. If not, go back, find it in the book, and make sure you do understand it. And in this chapter, there are 10 of those. Then there are 7 for further analysis. This just lets you think a little bit further along. And then there's some problems. Now, if you have the real text, not the little ones, the problem set A, group A, they have answers in the back. They didn't put the answers in the back of that. That's one thing I was really disappointed in. They didn't put the conversion factors in the front, and they didn't put the answers in the back. So I was sort of disappointed in that. But you can still look through these problems and see if you know how to set them up and do it. If you have any questions and you're not sure what you might be doing, I'll be glad to answer those. But that wraps up the chapter 1. Was there a question?
The 7th edition book it will be the same chapter.
Say that again.
The 7th edition book.
7th edition, that's a long way back, but I bet you it's the same because the science really hasn't changed too much. But if you have any doubt, check with your soldiers and make sure they read the same. All right.
How many questions will be on the first test from chapter 1?
It seems like, and I'm just going from memory here, it's about 10 questions, but several of the questions, most of the questions have multiple parts. So there's more than 10 answers. So you'll get credit for more. I mean, every question is going, if you miss it, it's not going to be 10 points off. Every part of it will be a certain thing. And here's another thing, folks. I want you to see you try every question. I sure don't like to see a blank answer. Then you miss everything. If you try something, show your work, attach your paper, especially this first test, and show what you're doing, turn in your scratch work. I would love to get partial credit. So if I see you're at least approaching the problem right, I can give you some credit. If it's a blank answer, that's 0 credit. Okay,
So will the test be based on what we went over in class, or is it more than just that?
it's a lot of, mostly what we went over in class. Reading the book is probably going to fill you in a few details here and there. But I think we've hit everything we did in class. So if you need to, we'll go back and listen to those YouTubes again. That's another good thing to do. Any other questions? What's that? When the test is going to be the last 30 minutes of the class on Tuesday. So it'll be, 5:15 to 5:45. Oh, no, 7:15 to 7:45. Sorry. 7:15 to 7:45. Okay. What time is it now, by the way? I don't have a clock. 5 what?
8 o'clock.
Yeah, right. Okay.
5:30.
5:30. Okay, still got 15 minutes. Why don't you stop me at 5:40 and we'll take our 5-minute break, and then we'll meet back in the lab that right next door at 2:53, and I'll call roll the second time. So let's get at least 10 minutes into chapter 2. Unless there are questions. Are there any questions on chapter 1?
So the parallel sets will be out.
It's actually
Okay.
5:35.
Yeah, right. Uh-huh. Yeah, I see it is. I see it. I've got it on my computer now. Okay, so we got 5 minutes of chapter 2. Let's at least introduce chapter 2. That's 5 minutes we won't have to do next time. See, I'd love it if we could get enough covered in chapter 2 so we could have the lab Tuesday, first lab on chapter 2. But right now, I've flapped my gums too much on this one, so we may not get far enough along. So that means we'll have a longer class on Tuesday, but we'll see. Okay. Okay. Chapter 2 is going to talk about motion. Big topic. Okay? We'll break it down into smaller bites. The core concept here, a net force, which we haven't defined what that is yet, is required for any change in a state of motion. Okay? A net force is required for any change of a state of motion. Okay, this chair is just sitting there, right? In order to get it to change its state of motion, in other words, move, I've got to exert a force on it. Okay? Either a pushing force, a pulling force, a twisting force. I've got to do something to change its motion. Net force is required for a change of state of motion. That's the core concept. We haven't identified what a net force is, or however, even how we measure changes in motion. So the first question is, what is motion? We need to know what we're talking about. So that we're going to start with describing motion, and that's going to be the next lab, not the one we do today, but the next one. Then we're going to try to explain motion. That will be the following lab, and then we may do some applications of motion, which will be, I think, the third lab in chapter 2. Now, if we get more covered than I'm thinking we will, we may only do 2 of those, but we'll see. So let's start with describing the motion. There's 3 basic concepts that go into motion. For something to have motion, it starts one place and winds up someplace else. If it stays at the first place, there's no motion, right? So it has to move. It has to move. So the first concept is position. In other words, change of position. In other words, in physics, we're interested in change just about always. Now, if we have a change of motion, a change of position, even on Star Trek, that took a certain length of time. So if you combine change of position with the change of time, that gives you speed or velocity. Now, what's the difference in speed and velocity?
Velocity is direction.
Very good. In everyday English, we use those terms interchangeably. But in physics, speed is how fast something's going. Velocity is how fast it's going in what direction. You're absolutely right. Now, in mathematics, we have two quantities. One is called a scalar quantity, just a number. The second is called a vector quantity, which has a magnitude, which is a number, with a direction. And guess what? Speed is a scalar, SS. Velocity is a vector, VV. So that's an easy way to remember, make a distinction between speed and velocity. Okay? Now, if you didn't catch it the first time I said it, position is distance or displacement. The time rate of change of position, divide position, change of position per time, you get speed, or time rate of change of distance is speed, time rate of change of displacement is velocity. Displacement is also a vector with a direction. Distance is just a length. Okay? Now, the third one is, what if you change your velocity? What are you doing? Accelerating. Right? Now, we normally, especially you guys with heavy feet, okay, you think of acceleration as just speeding up. But acceleration could also be slowing down or any change of velocity. Now remember, velocity is what kind of a quantity? Vector quantity. It has a direction. So if I'm going along here at 1 mile per hour in a certain direction, but change my direction, I haven't changed my speed any. Did my velocity change? Yes, because the direction changed. I had to accelerate to make that change. Now, where do you see that's true? Any of you ever been to Talladega?
Yeah, Omega.
Okay. And when they're changing direction, where do they do that? On the curves, right? And what do you notice about the curve? They're banked like crazy. Why? Because you have to have a force pushing it, an acceleration pushing the cars in. You try to make it, go around the curves at that speed when they're flat, into the stands, you're out. Okay, so you've got to have that. So yeah, acceleration is any change of velocity, whether it's a change of speed or not. So answer me this. What is your accelerator on your car? Is it the thing on the floor, the steering wheel, or the brake?
It's that
Thing on the
accelerator
floor.
pedal.
It's all three, because all three of those change your velocity. Your brake slows the velocity down, the accelerator speeds it up, and the steering wheel changes its direction. So all three of those are accelerators, believe it or not. I'm not going to say believe me. No, I won't go there. Okay. Applications we're going to do. We're going to look first at horizontal motion on land. We call that one-dimensional motion. Then we'll look at falling objects. Vertical, that's again one-dimensional motion. And then we'll look at compound motion, which combines horizontal and vertical. Any of you ever shot a basketball? Okay. How do they go?
In the net.
Two-dimensional. Two-dimensional motion. Okay. Golf balls? Yes, same thing. Okay, I bet you
Yeah, that's 5:42.
5:42, so we're going,
Teach for 2 more minutes.
huh?
I'll let you teach for 2 more minutes.
And no extra charge even. I didn't charge you a penny more for that. Okay, so we're in the process of describing motion. The next thing we're going to do is explain, well, no, this is still introduction, okay? So we'll do explaining is where we'll start next time. All right, good deal. I'm going to pause. There's 3 circles, and they're to draw the circles on a piece of paper, and then with a ruler measure the diameter in centimeters of each circle, okay? And when a team has 3 circles drawn of each size, stop. You don't have to draw more than 3 of each size, the whole team, not every person, the whole team, 3 circles, 3 sizes, okay, each. Then measure the, yeah. So if you have small circles, stop at 3 small circles. 3 large circles, stop at 3 large circles. 3 medium circles, stop at 3 medium circles. Okay? Now, everybody doesn't have to do all 3. The team needs 3 of each. Okay? Then once you, okay, you've got a large one.
We need 3 of these size, 3 of these size, and 3 of these size between all.
Yeah, between all of them.
Okay, I can.
Yeah, you've got one, and one. Okay? Yeah. Okay. Just be sure you got 3. Yeah. Yeah.
I need all 3 of them.
Yeah.
I need all 3 of them.
You don't need all 3, but yeah, you only got room to put down measurement for 3 of each size. So mark the diameter on each circle by drawing a straight line across the center, using your ruler for that, and record the measurements in centimeters. Okay? Okay. Be sure you got centimeters. Okay? And on page 23 of your lab, you see it? Page 23 of your lab, the small circle, each team should have 3 small circles, 3 different people took measurements, record the diameter in centimeters of those 3 small circles. Same thing for the 3 medium circles, and same thing for the 3 large circles. Got it? Is everybody following? Okay? You record that, yeah. Measure in centimeters and record it on page 23, top of the page, data table 2.1, diameter, big D. Okay? 3 small circles, 3 medium circles, 3 large circles. Now those 3 numbers had better be fairly close to each other, maybe not exact, but pretty close. I don't want 1.7, 1.3, and 1.5. Those are just not close enough. Okay? Measuring in centimeters. Put it on page 23 at top. Now, if you've already measured yours and recorded yours, and then wait for the other team members to do, here's what you can do. All right?
So which one you want us to put it back on?
Okay, there's large, medium, and small.
Under the trial?
Huh?
Under the trial, or
Okay.
which one?
You see data table 2.1, circles and ratios, right? The trial is 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? The diameter D, that's where you put your diameters. 3 diameters for small circle. Now that's 3 different people measuring 3 different circles. Okay? And then medium and then large. Okay? And each table now also has a meter stick. Okay. You finished with yours? You ready for something else? Did you record? Okay. That's what it says. Okay. You could write that 4.1. That'll be easier on calculation. Now, you'll get the. Okay. Now you share it. You get her measurement, his measurement. Okay, yeah, get them and write them down. You share with each other. Now, all 3 of you didn't have to do all 3 circles. That's not what I said. Go around until the table has 3 of each. You can use any 3 that you want to. Okay? And write those down. Share them with one another. And until you get 3 each. Okay? Now, the next thing you're going to do is this. Okay? Give me one of those circles. Okay. Could I get everybody's attention here for a minute?
Yes.
I'm going to show this team what to do. Okay, hand me one of those screens. Okay. Now, to get the circumference of the circle, hold the thing down pretty tight. Not too hard, these things are breakable. And find exactly where they meet. Pull this out. Takes some doing here, okay? And you need, thumbs are too thick, okay? to take this and stretch it out. That's your circumference of the circle. Take either your
No.
ruler if you can fit, or you might need the meter stick for the large circle and get the number of centimeters in your circumference. Did y'all see how to do it?
Yes, sir.
Everybody?
Yes, sir.
Okay.
He wants to do it for every size, right?
No, use centimeters. Everybody use centimeters. It used to be centimeters.
He said you see, yeah. Let me see.
Everybody measure in centimeters. Remember, that's the key.
Let me see that.
So what you're doing now is determining the circumference. Now be sure you put your circumference with the circle you got the diameter for. Make sure you don't, use somebody else's. Well, it doesn't matter. They're going to be close. Okay. Okay. I'm missing some of my lab materials. I don't know if my work study student didn't bring them up here or if they've walked off. So I'm going to, while y'all are doing that, I'm going to put this on pause again. You determine your diameters, you determine your circumference, and now you're determining the ratios, which is the circumference divided by diameter. The second one divided by the first one. Be sure you do it in that order. Okay? Let me go around and just look at your numbers. I did see one that was wacko. Okay, that looked good. How are your numbers? Yeah, they look pretty good. Okay.
To the 30 would be 2 and just. That's fine, because it's not
It's
gonna
fine. As long as you use the same circle, you expect to have some difference. Oh, it is.
Yeah, so those two. Sure.
That's right. I would say do 2 digits, 3 digits, 3.05.
Dr. Fowler, is that large one? Is the scale supposed to be out large square?
It's what?
A large cube? That's a small cube.
Okay, yeah, no. Okay, y'all are moving on, right?
No, sir, we're not.
Okay, so you got it, okay. Okay, right, okay. All right, now listen, if you got your ratios, you got 9 of them, how do you get the average of those? Add them up and divide by 9, see what you get. That should be something pretty close to those numbers, so go for it. All right, now actually this team with 5, since one of their people had to leave, if one of you want to go over there, you can. Now, think out a little bit, but it's up to you.
If you divide, if you add it on 9, divide it by 9, you should get the same thing. She gonna just add one for each group, and divide it by 3, and she'll come up with the same.
I was what?
No, not you.
The wall border.
Yeah.
Sort.
Gives me a hard time over here.
Okay. All of you made your averages? Oh, I've got one. I've got two. One scientific and one cheat. Okay. And I got it.
Okay, y'all come up with it. It's 3.17 or 3.27.
Is the average? Sounds reasonable. Y'all got your average yet?
Divided by 3. I mean, if you do the average, you take, if you want to average 3 things, you add 3 things together and then divide by 3.
Two to three. That's 3 to something. That's 3 to something.
I mean, it should work the same way if you added all 9 of them together and then divided it by.
Add all 9 together, divide by 9.
Yeah.
See the advantage of using pencil? Okay. Oh, yeah. Just see what
So we add all these up right now, divided by 9, that's the average, okay?
Okay. All right. That's it. Yeah.
Come here, tell me if I'm doing this right.
Okay.
Alright. I'm averaging these 3 out, right? Okay, so I'm not fixing to add on divided by 9. All 3 of these are the same. All 3 of these are the same. All 3 of these are the same. Okay. I should be able to add one for each group and divide by 3. Alright.
In general, that's why I was surprised they
It's
were
supposed to be.
all measured exactly the same. Even though they're same circles.
But when I add all of 9 up,
Yeah. 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 There you go. Ah, okay.
Hey, we got it now.
Okay. You got it.
Yeah,
Yeah.
you got it about it.
3.2.
Yeah, that sounds pretty good.
3.27.
All right. That's what's next. Now, I kind of doubt that number right there. That is not. See, this is way out of the. Here's what the problem is. It looks like you see 900%. Okay. Now, the question is, what's the experimental error? All right. Let me run to the classroom and get a marker. I don't know why there's no markers in here. I'll be right back.
I mean, I'm at 12. We had to be here at 8 o'clock this morning.
All right.
Hey, we had an hour lunch.
Now.
So, you know.
The question is, what's the experimental error? Oh, this marked better than the other board. Okay. What's the experimental error? Okay. Now, does anyone know what your expected value is? What the actual ratio of a diameter to a circumference is? Why is that?
That was a good.
Yeah,
It's pi, exactly. All right. So we know the answer to two decimal places. The actual value is 3.14. You've got a measured value of something, and it should be pretty close to that. Okay? So what your error is, this is error, is measured minus actual. If you measured larger, you got a positive error. If you measured smaller, you got a negative error. So this is your error. Okay, now does it say error or does it say percent error? Let me see what it says. You're following the questions on the page, and that says, oh, and by the way, at the bottom of page 15, number 4, the ratio of the circumference of a circle to its diameter is known as pi, which is 3.14. Average all values and calculate the experimental error. That's what it is. Measured minus actual. What you measured when you're average minus 3.14. That's your experimental error. Okay?
you said 3.14 times the average, right?
No. You're measured. What did you measure? What was your average of those 9?
Uh-huh.
What was it?
Average.
What was it?
3.12.
Okay? Minus 3.14.
Oh, minus.
Yes. Okay. Now some of you are ready to start on the blocks.
Let's do it.
Okay. Now each team has only one block. Okay. First thing you do is take your booster, and however you want to do it, measure in centimeters. In fact, let me see what it says. Okay, it doesn't say what units you would use, so I would suggest centimeters again. Okay? So what you do, and you may actually want to draw one. This is not a cube, by the way. It's a rectangular parallelepiped, which isn't a cube. But, you can do it. So what you do, and ignore the holes. Ignore the holes. So measure each side to the nearest tenth of a centimeter. Okay? And then record those. And I would record it as length times width by height, or something like that. Okay? Okay? Okay, now, did you do measured minus and this actual?
Yes. And it
No, your measured was bigger than the actual.
I told him.
Well, then that's a positive number.
I
Okay.
told him. I said, but he said no. You got to. I said it should be a 12 to 13. I said,
Okay. 0.13. Other teams may have had negative. I want to know what y'all got. Okay.
Mr. Fowler, what do you
Okay. So next with the block. Okay. Let me borrow your block for a second. Okay. Here's a block. Ignore the holes. They're not important. What you do, it's not a cube, by the way, but with your centimeter scale, measure, however you want to do this, each dimension width of the block. Length, width, and height. Okay? Record that somewhere as scratch work. Length, width, and height. Is this mine?
that's you.
I think so. Okay? Now,
We're gonna, can we do that? Can we do that in inches?
no, let's do centimeters. So everybody will use centimeters. Record that in centimeters, but do it to the nearest tenth of a centimeter, each dimension. Okay, now I'm going to draw a picture. My pictures sort of stink, but I suggest you do something like this too. These ends are almost square, right? and then they're a little bit longer this way. Okay? And then you have a square back here. So I would record what your length is, your width is, your height, however you want to do it. All right. The next thing you've got to do, okay, is, all right, now you can't follow what they say because they're dealing with cubes. You have to do what we're dealing with, which is this rectangular parallelepiped, okay? Whatever that is, okay? Now you'll notice that however you face it, the square sides are equal, right? So take the area of that square side. That's this length by that length. If they're square, those two lengths should be the same or pretty close to it. Multiply this by that, and then double. One for the front and one for the back, right?
I'm sorry, I was trying to meditate at the same time.
Okay. All right. All right. Listen up. Okay. Have y'all got? Okay. What you do is you've taken your measurements. Two of these measurements are really close to each other. They may be exactly the same. And you see, if you multiply this measurement by that measurement, those two that are close to each other, that gives you the area of this face. And that's exactly the same as the area of the back side, or whatever the opposite side. So whatever that area is, you double it. Okay? Now, these sides should be about the same too, right? Measure this times that. That gives you the area of that face. But how many of those do you have? 4. So multiply that area by 4, and that's going to be your surface area back here on the table of your small cube. Surface area of the small cube. So measure length, the two sides that are close to each other, multiply those together, double it, hang on to that number. Then one of the short times the long, that gives you the area of that side. Multiply that by 4, and then add the double thing to the 4 thing. That's going to be the total surface area. Right?
That's your total surface.
Yeah.
So hold on. Say that one more time. Each surface.
Okay. Okay. The surface area of this face here, the one that these sides are almost the same, or maybe exactly the same. Multiply this by that, and that gives you the area of this side. The back side is just like it, so double. Okay, whatever it is. Okay, then do this side by that side. That gives you the area of that one. But that's the same as that one. So multiply that by 4, and then add those two together. Double this. Let me see where you write down on this. Okay. 3 by 3 by 4, is that it? Okay. Well, 3 by 3 is? Square. Okay. Is that 3? Okay, by this one, is that 3? Okay, 3 by 3 is 9. You double that. That's not 12. These two are the 12.
Alright, 3 by 3. So you're ready here?
Say that again. I don't know. They got 3. You got 3 by 2, 3 by 2, 3 by 2. No, I didn't say that. Oh no, I said measure the nearest center. Okay, and you did. These are great measurements. So 3 by 2 by 3 by 2, that's your square side. Put it in the area of this. You got 2 options, so double that. And then you got a 3 by 2 by 3 by 8. That's this one. And then multiply that by 4, and then add the double to your 4. You got 4 sides. One side, this square right there. Okay? And then you double that.
Times 2.
Times 2.
Okay. This right here is 4.
Yeah. That gives you the area here. Multiply by 4, and add those two together. Double it together. That gives you total surface area. Y'all got it? Y'all are on this next thing. This is what you're doing.
He's copying me. Look, not doing any work. At least I was when I did it wrong. At least I did work. You copied work.
He said that,
He's someone better than copy. Yeah, I mean,
What's he thinking?
he ain't got anything in his desk.
Hey, coach, we don't have a long. That's one.
that's small. I'll tell you about the next one in a second. Yeah.
1 second, please.
Okay. Wait a minute. This times this to get the area. How many feet? This times this. 3 by 2 by 3 by 2. That gives us area this side. Multiply those two together. 3 by 2 by 3 by 2. Okay. And then that picture, you multiply 3 by 2 times 3 by 2. This length times that. That's the same.
Okay,
That's
okay.
3 by 2 times 3.2. Okay. Get what number that is. And then it's going to be something close to 10, plus or minus 2. And then whatever it is, double. So you got to put
Whatever
that
this
on the back
answer
side.
is times 2.
Yeah, exactly. And then you do 3 by 2 times 3 by 8. That on this side. You do that 2 here, so 3 by 8 there. Which is the same as that. Same as that. Yeah. Got it. And add it together. Yeah. Any questions? What's that? Show me the. Okay, right. Okay. You're saying this is 3, that's 3. So when you multiply those together, you get 9 squared. 9 squared 2. Double that because you got this side over here. 3 by 3. Now, this one is 3 by 4. And then you multiply that by 4 times.
12 times 14.
Huh?
No, 12 times 14.
No, I know what I'm
No,
talking
no.
about.
Yeah.
I know that plus the 18.
Plus the 18.
It's 66.
Yeah, 66. Okay. That's your total surface area of the small cube. Because right there. Okay. Square centimeter. Square centimeter. Okay? Everybody got the total surface area of your small cube. Okay? Let me see that. Let's see if I can. Okay, first you got 6 centimeters square. Okay? And let's see, how did you get it? Where's your measurements anyway? Oh, here's your measurements.
Oh, yeah.
Okay. Okay. You got this. That far. Okay, let me see that. What?
Do the volume by.
I'm dividing it equally.
3.1? Okay. Do that. Yeah, those two are the same. So multiply those together, it's going to be something a little bit greater than 9. Double that. Okay. Double it because you got a front side and the back side. Double whatever, it's going to be more than 9, but yeah. That is, huh? Times 6.1. Okay, double that.
Times 2.
Times 2, so you got this side and that side. 9.2. Okay, write that down somewhere, not on your answer. Right. And then you do this side. You say 3 times 8, 5, 3 times 9. Okay. That will get in the area of this side, right? No, times 4. Because you got 1, 2, 3, 4. And those two together. Then you're pretty close to what you have. Good bad. Pretty close. Good deal. So you were right on the money. Okay. Okay, everybody got the surface area of your block? Okay? Next, before we move anywhere else, what's the volume of that block? What is volume of the block? Volume of anything. Regular, parallel height. Volume. Okay? That would be length times width times height, or length times width times height. That's it. Multiply those three dimensions by each other.
Length times width times height.
That is your volume. Yeah. Yeah. 9 times 4 is 36.
Okay. So that's 36.
Okay, write that down. It's cubic centimeters. That goes on volume of the small cube. Okay? Then you do the ratio of your area to the volume, the top one to the second one. And write down what that area is. Ratio meaning what operation? Divide, exactly. Okay.
I don't know what, I just got 0.5.
That could be. No, it's this one divided by that. Surface area divided by volume. Okay. Okay. Now, I hope that everybody wrote down their dimensions. Now, I'm going to make up dimensions that I know are totally wrong. I'm going to say 4.2 by 4.2 by 5.3. Now, I know those are wrong, but I'm just going to use them for an example. If that was your original block, your small block, and they're wrong, don't use these. Okay? Then to get the next size block, you double each of that. So double that, and double that. So your new dimensions would be, no, these aren't yours, 8.4, 8.4, and 10.6. Okay, those are your new dimensions, and then you go back. Now, don't use these numbers. Use your numbers. Yeah. Okay, don't use these numbers. But double them, those are your medium block. Exactly twice in every dimension of your other. And then you do the same thing you just did. Multiply these two together, double it. Multiply these two together, and multiply it by 6. Add it together. That's your surface area. Right? Did I say double those? No. I said write down your dimensions, double each dimension, get your new dimensions, and then do the same thing you did before. Yeah. You wrote them down somewhere, didn't you?
Yes.
Okay. That's on your piece of paper too. You know it. 3 by 3 by 4. But now this new one, that's this one. 3 by 3 by 4. No, that's small. Okay. And I'll double each of those, and that's your new medium. Up here. Okay. That would be. No. 3 doubles is not that. 6 plus 6. 8. You got it. Now with those dimensions, go back and do your surface area, and go back and do your volume. Remember how you did the surface area? Multiply these two and double. Multiply those two and multiply by 4. Multiply the short 2 and double that. Multiply the long by the short and multiply by 4. Add those together. And that's your new surface area. That's the medium surface area. What's that?
Just tell them exactly what we're doing. Okay, so you took three, four. Together. Next
Double.
one, I'm gonna start the medium.
Oh, so we're doing medium cube
Right.
measures.
So it's 6 by 8.
You just double each dimension and then recalculate the area by it.
Shouldn't you just be able to multiply it into the number of 4 or 8?
Or something.
Is it 4?
Okay. Good thinking there, because what you're doing, you got another block on top here. Okay, this doesn't look too good, but okay. And you got another depth here, and you got another depth here, but then you got another one here, and another one here. So you got. Okay. Yeah. Picture this. Okay. You double that, and you double that. So there's 4 on the bottom, and then you 4 on the top. So that's 8. Right. That's doubled everything. Huh? It's not 9. It's 8. Picture this. 12. You double this dimension. You also double this dimension. From the bottom, you got 4, but you double the top too, so you got another 4. So that's 8 times 4. That's your body. But does that mean that's your surface area? Huh? No, because you see, all these interior surfaces, yeah, they're not going to be that. So you have to, the easiest thing to do, is just what we did before.
Did you want us to round all that? Or did you want us to just round
Okay. You really only need 2. It'll be actually 3. You only keep the top 10. Wait, for the interior. Wait. How are you all those digits for the thing? Your answer, what you write down, that's the ground. And it's okay.
Because 66 was the area.
Okay, when you multiply all those together, you get that. Okay. Now, once you check the other thing, check your volume of the whole by 8.
We've got.
All right. But that was cheating a little bit. That's just first. So that's yeah. So yeah, 311 more 3 is fine. Yeah. Right. That's perfect. Okay. But yeah, doesn't work for the surface area.
Yeah.
It works for the volume, but not for the surface area. Surface area, you have to do it the way we did before. Okay, yeah, it's the, give us the block. Okay. You use the whole. Here. Okay. Oh, yeah, this is that, okay, here's the new, what is it, 6?
I don't know if that's right, if I'm like, wait,
No, I mean, watch it.
I got 260.
Do here, and then you say, 4 times 4. Now that ratio, you don't need to use like you said, that's fine. Actually, it has centimeters squared per centimeter. All right, all that. Yeah, that's the one that I'm going to be able to do.
I could approach it and you add it and then you add what you get. Plus you said you
Double that. Yeah. Wow. Hey, you will work.
Now for your bottom, you will do.
It's 288 centimeters.
Okay, your surface area. Now you build the, you go 4 times.
36
Clean after.
times 2.
I'm like, I'm
And then, I mean,
You're
you're 72. Hey, what are you trying to do right now? She'll eat, she'll eat and drink, and I'll watch TV. She'll eat and drink, and she'll like put her paws on the couch. Oh, I don't know. Alright, come here. What you doing, puss? Fine, alright, go to sleep on my chest, that's fine. Yeah, I can't move until she moves. I do not want to disturb her.
How do you want to do the large?
Okay, the large. Guess what we're gonna do for large? 3 times that little one. So if it was a 4.2, 4.2, 5.3, that would now be 3 times that would be 12.6 by 12.6 by 15.9.
So 3 times, so now we got 6 and you want to go 3 times.
Okay, 3 times is small.
Oh, 3 times is small.
3 by 3 by 4, that would be 9 by 9 by 5. Okay, y'all heard how to do the large?
So,
Still working on that?
here we go. You do 9 by 9 by 12.
Very nice.
Hey, look at me
9
go.
by 9 by 12. So the first one is 80.
I made something. Okay.
Get out of here. Get out of here.
I heard what you called me.
You still on that train.
So 9 times 12.
Very smart. Man.
Okay, wipe it off, wipe it off.
Yeah. My nose about to start growing. I call what they said. Heard what you said.
So it's 8,000.
Okay, you know what the large cube's gonna be then? On my dimensions by the way.
You did 81.
Just these.
Yeah. That'll be your new one, then recalculate again.
Then 108 times 4. That's 181 times 2.
Right?
That's the deal.
That's what it sounded like to me.
Times this.
Right. Okay, okay. Okay. Now you do this. You like to get your arms.
Okay, let's do that.
All right.
Yeah, it's just a top number.
The first one I got .091.
I think it's assumed.
Let's stop that number.
Okay, yeah.
Let's close that. Let's close that.
Let me just check. You know, I'm just
Yeah, I took this one. Exactly. We are right in the 80s. It would be centimeters cubed.
the volume of centimeters cubed. All right. Now, these down here are not. The actual units here, centimeters squared per centimeter cubed, which is 1 over a centimeter, which is such a weird unit. Or you could say centimeter cubed per centimeter squared. either wipe it out or put it in minus one. One over a centimeter. Now, you ready for your third one? Yes.
Give it to us, Coach.
Okay, now you flip over.
So,
You attach the other two. Now, you got this box here.
160.
Somebody booted that. Now, get your measure, okay, and you're going to do length by width times depth. Now, if I were you, I'd say this was the length. Now, you notice there's a slant there. Now, how we accommodate that and get it in centimeters, okay? I would go halfway up it and halfway, look at that.
Yeah, I know.
Yell out, that's length, width, depth, okay? We'll do that. Okay, now put yours over here on your computer, okay? You'll get the small box, you'll get the data from them.
I know I look like I
The,
said,
under one, and the medium under two. So you do yours over here. Okay. Good deal.
Okay, Mr.
Look at that. All right, now, I think all three teams are ready for the last phase, right? There you go. Okay, for your last thing, each of you have a little box. They're all different. Okay? Now you folks will put yours under column number 1 on the back side. Okay? Y'all will do it on column 2, and they're doing theirs on column 3. And when you finish, you're going to share data with each other. Okay? So the first thing you do is, now notice these boxes are not quite square. So what you do to do is go about midway up here to midway up there and measure to the nearest tenth of a centimeter. That's the length, the width, and the depth. Okay? You can take this lid off of there and do that depth there. Okay? Times depth. And that's what you put yours is on your second column. To the nearest tenth of a centimeter. Okay?
The length is going to be.
You said about midway, right on the first.
Yeah, and I would go midway up so you sort of have a shot. Yeah, that's good.
That's the next.
I dare you. You made the thing. You gotta pay the thing. You could have said that better.
Once you get your length, your width, and your depth, then multiply those together, get your volume. Calculated volume, that's number 4. Y'all got it? Okay, all of you don't have to do it, you can share data. You're working as a unit, as a team. If you trust me. That's a big deal. All right. Okay. Then you multiply those together and get your calculated volume. You've done, right?
So that's
Okay,
like
good. All right.
Multiply together.
Huh? Multiply those together. Volume. Okay. Now the sad news here is we only have 2 scales. Okay? Sir? Y'all got it? Yeah. Good deal. Okay. Now, sad news is you only got 2 scales. This team doesn't have a scale, so y'all will be using this as soon as you finish. So you put, okay. First thing you do is 0 the scale. Make sure that's lined up to 0.
It just so happens to be one off.
Okay? All right. Now you put the. All right. Then you put your container on it and find the mass of the container. Measure that. Each little dot there is a gram. So how many grams is that? say whoever did zero and should probably make the motion. Yeah, well, that's 10, yeah. Okay, well, that's fine. That's not gonna hurt. 10 grams is fine. Okay. Y'all hear what you're doing?
We just gonna wait.
Zero the scale.
Whatever number zero.
Okay, so all are, well, they've already done theirs. Yeah, okay. Okay, y'all move yours for a second so they can use it. Zero the scale. Yeah, you can use it. Either way. Let's go on the middle.
Let's see, it was 14. 10 grams.
Yeah,
That's good. This is good. Let's see.
okay, put that on. Measure the mass.
Maybe it was 3.4.
You already measured the mass of your container? Or you haven't even calculated your volume, huh? Wait, did you zero the scale first?
Yeah, yeah.
You did. Okay.
Let's what you're saying. 600.
So what's it saying?
Right here. That'll be in your.
30.
Okay. 30.
You'll check it.
Okay. Okay.
That's 30 points.
Now, this next step is a little tough. Okay, yeah. If y'all, since yours is on there, you can go and do yours first. Well, yours is the smallest. Open your box. Alright. Now you need to be very careful here, people. Put it on the scale. Alright. Now start slowly pouring water in it until you fill it. I would say leave it on the scale. You don't have to stay on there.
Sit it on the scale.
They don't be leak sauce. Leak sauce.
Slowly fill it until you got it full.
So you
Okay.
leak sauce. Water sauce.
Come on, let's. What you got?
Leak
Let's
sauce.
get it up back to you. What you got?
Where?
Okay, I would suggest y'all pick up your paper. Because this is going to be potentially messy.
110 grams.
Okay, it's not full. Fill it all the way. It's up to you. Okay, wherever you think it's full, you do. You know, before you go to the next step, hey, especially you, before you go to the next step, let me go get a bigger container because you're going to need it. Oh, hey. Be very careful with this because this is glass. I don't want it broken. I'm borrowing it. So did y'all know it? You sure you can't put more in there?
You want to do it till like.
Okay. Okay, wait. Let me get something bigger for you to pour in. All right. Now, you don't want to squeeze it much. In fact, I say just hold it as close as you can. Y'all want to do the best you can to get it all in there. Okay, y'all can start working on your.
Make it to the six, make it to the six.
Okay, you already got the message you take. Okay, I just want to ask you a question. Have you noticed you can actually move it? Do you know why that's true? Yeah, it's called surface tension. Surface tension. So yeah, y'all have demonstrated that very nicely.
I know.
Now who's going to pour it into the container?
It's 100.
Yeah, well,
So we
that's
gotta
there,
get the mask
very,
up,
very
the
careful.
mask up.
By the way, before you do anything else, physically, okay. Yeah. All right.
Nice water, you had a lot of sand right for you.
I tried it.
Okay, I think we've introduced a little experimental error. Okay. Now, wait,
We can even it out.
okay, wait. Let's dump everything and try it again. That's why I gave you on your own scale. Okay. Okay, I think your paper question's out there, someone runs a question. This time, let's plan for it so that we can, when we get the floor, we can just dump it this way so you don't have to do it. Don't tell you, y'all already said that. Y'all use that. I'm nervous right now. Okay, you got anything that can melt? This is the table.
For your mass, the time with the mass award is 107.
Whoa!
Okay, we got the 170 grams for mass award.
Okay, now.
Yeah, I got it. Yeah, you're about to stay. I got a portion to it.
Got that right here.
All right, that's it. As long as it doesn't touch the top. All right.
We can reuse this. Dough. Dough?
Yeah, he's coming. Yeah.
Actually, I don't think. Children, Jesus
Right,
Christ.
right.
You close the lead.
Right. Oh, the crack, oh, I'm sorry.
Yeah.
Yeah, okay. Probably.
How did we get that much in there the first time?
Okay.
197
Okay, no, you don't use that. You get all your water? Okay, not that, you got it all, right? Okay, we got that. Well, that is very much, this is far more precise.
Oh,
There is experimental error. Okay.
We don't see no more.
Oh.
We did.
Alright, got it? That's it, okay.
Okay,
Okay, get that one out of the way.
Y'all can do it.
Well, we already had another.
Number 7.
Can't even dig it up.
Oh.
Can't really do the volume 2 yet.
Because y'all have so much water, you're gonna need to do both seats. So don't fill either one of them past the maximum where you can read. Fill only, don't exceed this mark, don't exceed that mark. Pour it in, you have to add them together. So you pour from there to there, and see what you get. Okay.
Okay, we got.
All right. Y'all got it? Okay. What you'll need to do is very carefully take this and get it to there. Okay? Try not to spill. It's going to be very hard not to spill. Yeah, pick it up where it has. Okay. Now you see why you overfill a little bit. Why you got a little bit. Okay. Now you empty this. Did you empty that already? Oh, there, I'm sorry. No. Measure that. This is very imprecise. That's much better. Okay, we'll try it. No, you don't need it. We'll see what you get. It may come up right there, but there it is.
245 and 219.
That's gonna give us, one.
Under that's a lot better read than 200. I mean, a little bit better, not a lot. Okay.
Water plus water.
How do you add water? That's,
Have you added those together?
that's 150. It's 170.
245 milliliters plus 210 milliliters. I bet it equals 155.
187, I'm sorry. 187. 187.
Yeah, or it's Slim Jim.
It's 187.
Okay.
It's 187.
187, I would say that's a lot more precise than 200. Okay. Now, okay. Now, what I want you to do, since you got your data, y'all are the small team, so I want you to read out to the other two teams and put under column 1 your length, width, and height.
Okay.
Y'all listen up? Okay. That's all. Length, width, and height.
Your length is 8.9.
Okay.
Width is 4.2. Height 3.2.
Okay. Number 2. That's you guys. You read out your length, width, and height. Oh, you're supposed to write those down.
Oh,
Right. Right down.
Column 1.
Column 2 is, length is 14,
Okay.
width is 2.5, and height is 2.5.
And
Column 3.
the big boys, okay?
The length is 16.3, the width is 8.6, and the height is 3.4.
Okay? Little one, give the mass of your container, number 5.
6.
6 grams.
Uh-huh.
Medium,
10.
10 grams. Large,
6.
30 grams. 30 grams.
Yeah, 30.
Okay? Mass of container of water, number 6.
119.
119 for the number 1.
196.
196 for number 2. 4. Mass of container of water. Second. What's number 6? Have y'all gotten that yet?
Come on, group 3.
No, the mass. You read it off the scale. You didn't read it off the scale? Wait a minute. Okay, put the thing back on there. No. You have to put the container back on there. Pour them back. You don't have to change them again. All you have to do is get your mass. All of it. All of it.
Oh,
You got it all out of there, so you all better go back in.
Random.
All of it.
you don't think they're random? I still fit in there.
All right, what's your mass?
What is it?
What?
72.
72.
That's
72.
It's like 172. That's 472.
472.
What?
All right.
That's 450. Why'd you say 72?
Okay. Large container number 6 was 472. Is that right?
Yes.
Sorta. Okay.
Hold on, I'm sorry. What now?
Mass of the number 3 mass, number 6 to number 3, number 3 for number 6. What was it again?
472.
472.
470.
Okay. Now the rest of everything you can calculate on your own.
Right.
You don't need the other people to do it.
Right.
Okay. Need a little energy, right? Huh?
I'm ready to go.
Yeah.
I've been here since 8 this morning.
Oh. three 3-hour classes, and this one 3.5-hour class, and then the 2-hour, 2.5-hour class.
From here, if I do, you'll know.
Number 4 for column 1 is 11, 6.16.
Buy me lunch.
Let me make it
That was Curtis Mitchell.
Yeah.
Oh, so
You still got the measure volume of water from everybody?
Oh, measure volume of water, I forgot that one.
Yeah.
Number 1,
100.
100 milliliters. Number 2,
97.
187. This is number 8.
Oh, but it's
And
already.
then number 3,
245.
245.
What did everybody get
The mass of water you subtract 5 from 6. So mass of container minus mass of container water, that will give you mass of water.
percent?
187, I'm sorry.
You got 113 and 442.
Calculated volume, multiply the things together like we did before. How we coming? You got it finished?
So far.
Would that not be 0.1?
Oh, wow. That is
Oh,
8.9.
yeah, okay.
Hey, Tiffany, come here. Come here. Zach. 8.9. First column, no.
You get calculated volume wrong.
That's 8.9.
When you did 1,000 something, I was like, yeah.
Equals 119. 119.616.
That sounds more reasonable.
Yeah, 119.
So 6
Yeah. 119.6.
let me try, let me do that. Yeah, that's good. That's how you want the ratio?
Okay? Now, okay.
Alright, let's make a little really low. It was right there.
Now your ratio of calculated volume, that's this one, to measured volume, this is that. Is that right? Oh, where did that? See, y'all are getting that. Where did y'all find that?
I just, I got it right there by the
Oh, I
microwave.
see, okay.
You said that times?
No,
Divided.
ratio, divided, right.
Divided by.
Yes, you may.
Okay.
Ratio from number one is.
Okay.
Ratio from number one.
They're adequately dumped. Okay, that's fine. All right. Good deal. Very nice. We need one more block.
Okay, big fries over at the big table.
I'll never get it straight again. Thank you. What's that? Yeah, okay. I know that we still got about 15 minutes, so I just wanted you to understand what's going on now. If y'all finish the table 24 on page 24, if you go back to your instructions, okay, on the mass and volume ratio, you've done number 1, that's on the bottom of page 16. Number 2 you did, that was on 17. Number 3, number 4, number 5. Flip over to the next page, and it says make a graph on number 6, top of page 18. Make a graph of the mass in grams, that's the row 7 data, and the volume in milliliters, the row 8 data, to picture the mass per unit volume ratio found in step 5. Okay? Okay, exactly. Okay? All right.
And this, what you said again, make it.
Okay, it's printed at number 6. Number 6. Okay. Okay. The graph paper is on the very back. It's printed on the back of page 24. That's what you're going to do. The row 7 data. Okay. 113, 186, and 150. Well, that's not. There's no decimal in there, is there?
No.
Okay.
That was a script.
Okay, 1573.
Picture the mass per unit volume ratio down.
That doesn't. Go
The
ahead,
volume on the x-axis.
Okay.
Horizontal.
This thing minus that thing should be that.
Okay. And the mass on the y-axis.
This is mass of water
The
minus
mass
mass
and
of
volume data
container.
from each container will be a data graph, so there will be a total of 3 data Well,
And I really doubt
it says
your number. 8
7
data too,
data.
folks.
Which
You had water in 2 of these things.
row, 8 data.
Yeah, I think it was a 445. It sure was.
We were supposed to add these together.
Yeah. I thought you were writing in your head, and I thought somebody else was putting on a calculator. Y'all were betting on what you got it.
You want X to be,
That was at 245. That was at 245. That was at 210.
Okay, now let's do it.
why gonna be up here? So we'll be fine.
Mass and body
Okay,
each is
so I'm
the
gonna have
same
to,
data set.
Okay, tell everybody else. Number, on line, road number 8, number 3 is 455. If you write down 2, whatever that was, 245, that's incorrect. 455.
What's the board name?
Eight,
Oh, Pat.
Road 8.
Pat.
Pat.
Actually, call that. He should
Row
call
8,
that.
which one?
Instead of
Road
245,
8,
it's
number 3
It's what?
is what was it?
What's the number?
455.
455.
Thank you, Dustin. 455.
455.
Pat. Pat, you should have came across on
Yeah,
that.
you bad.
You're a big boy, man.
That was sad. That was sad.
Come on,
That
Pat.
was sad. No, never
Pat
mind.
should- Pat
Come on,
should have
Pat.
before it came up. So now.
It's the file.
Yeah.
I added it, and he even added it.
What time is it?
Hey, you didn't double check the signature, so it's partly.
Okay.
It's not my fault. It's not my fault.
Okay. Hold on, folks. I know
Oh, who's that?
we're getting close to the witching hour. So here's what we're going to do.
Number 3.
I'll answer any questions you got now. But what we'll do is, and I'll give y'all a choice on it. You want to finish the lab first thing Tuesday, or have class and then do lab and then do tests, or how do you want to do it?
Because he gotta leave, right?
Okay, this, Route 1, we got this.
Okay.
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 We already got one.
We did this.
Okay.
We
Now,
got this.
so what we'll do on Tuesday, if y'all don't have a preference, we'll finish the lab first, then we'll continue with chapter 2, and then we'll have the test on chapter 1.
I'm saying,
No.
at 7:45, you have to leave.
I know.
I'm good right now.
Okay.
7:45, I gotta go.
I think we did this.
Okay.
Okay, let's go ahead.
Okay. All right. Well, let me see what their question is. Okay. Okay. Now here's what you do. Y'all give me. Okay. Y'all give me the. Fill it up very.
Where our axis should go, X and Y.
Okay, right. Yeah. That's what I was just going to say. I would like for somebody to read real quickly to me.
Okay.
I got them right here.
Okay. Let me get the order here.
Man, I think we could cross this to see what it is.
Okay. The volumes on the x-axis or the horizontal axis give me volume.
Route 1.
Row 8 data. Tell me what that is. Those 3 numbers you got.
It's 187, 187, 455.
Okay? And your row 7 data.
113, 187, 442.
Okay. Really not going to matter too much. I think your horizontal data has a little bit better. So what I would suggest, not necessary, but what I would suggest is do it this way, landscape. Okay? Now, give me your minimum and maximum of those.
You did, minimum
Up
is
to
455.
455.
Right.
Okay? So, 1, 2, 3, 4, 5, 6, 7, 8, 9.
9.
Okay. Yuck, it's so close.
Should've been 10.
Let's just do 0, 100, 200, 300, 400. No. Do it this way.
Do it in
No.
100.
Get it by 100. 100, 200, 300, 400, 500. Okay? You're not going to exceed 500. And then vertically, 100, 200, 300, 400, 500. Okay? So set up your scales that way. And what did it say?
100. Same way.
It said the volume on the horizontal axis, that's your row 8 data,
Correct.
and your mass on the vertical scale, that's the row 7 data. Okay? Now, someone give me that first ordered pair.
First order pass, volume on row 8.
Okay, volume is
100.
100.
187, 455.
Okay, 187
455.
and 455.
Right.
Okay? And your mass,
Mass on row 7, 113.
113,
187.
187. Look at that.
442.
442. Oh, y'all are got some pretty good data here. Okay, what you do here, you see where 100 is, that's right on the tick mark, right? Okay? That you go over to that first block and then go up to the 100 and then go up 1.3 above that. Okay? You see? 100 and then 1.3 above it. That would be a little over 1, but not halfway to 2.2. And that's your first point. This next one, you go, that's 100, go over almost to 1.9.
100.
Okay, and then go up 113. No, up, there's 100, there's 1.1, and then just a little past 1.1. On the 100, on the one that's right there. Oh, yeah, just above the 1. No, just above this. The next one, that one right there, just above that.
That's 10.
That, yeah, 110, 113. There's your first point, and then 187, so that'd be 1.9 almost over and 1.9 up. Just about, very close. And then 4.5 over and 4.4 up. Okay? Okay. Yeah. 100 is your X. So that's it. It do just over 1.1. Good. Okay. Now 187 says 1.87, so almost 1.9. Now that's 1.8. Almost 1.9. That's 1.9. It goes up 1.9. Almost 1.9. Right about there. Right there. Right. 1.87. Oh boy, big time. Okay. Okay. Better use pencil, by the way. 4.55 across there, so it's 4.5, almost halfway between 4.5 and 4.6, and go up 4.4. Okay, now get your ruler. Oh, they already picked up your rulers.
Yeah.
Okay.
Yeah. Hold on, which one am I missing? Are we showing volume and mass?
Mass and volume. Mass on the volume on the horizontal scale, mass on the vertical scale. Okay. Now,
Mass is on horizontal.
we've got only a minute left. We can finish this next time if you want to. Okay? Now, that also means
That's on horizontal.
you can work on it on your own some. Because here's what we've got to do. And this is going to take a while. So I'm not suggesting that you wait till next time to get started. And by the way, on other number 6, there's a big blank. That means you write an answer in. Okay? That's on page 16. Then starting on page 18, everywhere you see a big blank, you need to write an answer. Page 19, you give overall results of the entire lab. Not just what we did, but what you've learned from it.
So, are we working on our own, or will we have lab on Tuesday?
We will do some. We'll be in the classroom. We're not going to come back here on Tuesday, but we'll be in the classroom, and we'll work on the lab until y'all are satisfied. You got pretty much understood, and then we'll continue in chapter 2, And then we'll have the test on chapter 4.
Mass is horizontal, volume is vertical.
Exactly. No.
No?
Volume is vertical, mass is horizontal. If you read that number 6 at the top of page 18, it says, see,
So then I just take
put the volume on the horizontal axis and the mass on the y, vertical axis.
This right here is.
That is volume. This is mass that way. Good deal. Y'all did pretty well.
I shot a water paper.
All right. Have a good weekend.
Thank you all.
Oh my goodness. Okay, I'm missing one.
Yeah, photos. That's that bad.
No, I'll pick them up. Yeah. Some team had. Oh, yeah, I already put it there.
I'm putting you a charger back in your bag. Okay?
All right. Have a good weekend. And this was over here. Okay.
Thank you.
So have time for questions on team.
That was wonderful.
That's super to hear.
It was good. It was fun. Very educational.
And you work together well in
Yes,
groups.
it's a team. Yes, we did. Thank you.
I can tell this is going to be a good class.
You have a good one.
You too. Thank you so much. Yes.
If I go back there, I'm on the far end of this building part. Can I go out those doors that says have to stay closed? Can I go down these steps right here? To get out to that parking lot?
Now, is that the little bitty parking lot right against the
I'm at the main entrance if you come through the glass doors.
Oh, no, that's this one.
No, it's in the home parking.
Let's go, Chick. Let's go, I'm going out. Let's go.
Okay.
You go.
Cause I'm where it said the big sign said A. And I came past all the offices and all that.
Yeah.
Uh-huh.
Okay, I'm pretty sure if the big glass doors and that first desk.
Yeah.
Yeah, okay. Probably the easiest way is pick one half dozen of them, either that playground or the one
Okay.
And